65 million years ago, on what geologists would eventually call the Yucatan Peninsula, the morning began like any other in the late Cretaceous. Pterosaurs wheeled above coastal marshes thick with flowering magnolias. A Tyrannosaurus moved through stands of primitive palm, its massive head swinging left and right as it tracked the scent of prey. Somewhere in the shallow seas that covered much of what would become North America, ammonites with shells like coiled rope drifted on warm currents, filtering the nutrient-rich water. The dinosaurs had ruled this world for over 160 million years. They had survived volcanic winters, shifting continents, the rise and fall of inland seas. They had adapted, diversified, conquered every terrestrial niche from the poles to the equator. And in that particular morning, as the sun rose over a world that seemed as permanent as stone, not a single creature on Earth could have known that their extinction was already hurtling toward them through the absolute darkness of space. The object was roughly 10 kilometers across, a mountain of rock and ice that had begun its journey in the frozen outer reaches of the solar system, in that vast and sparsely populated realm we now call the Oort cloud. For millions of years it had drifted there in the cosmic deep freeze, one unremarkable member among trillions of similar bodies, all of them remnants from the solar system's violent birth 4.5 billion years earlier. But something had disturbed this particular object. Something had nudged it from its stable orbit, sent it falling inward toward the distant warmth of the sun, and as it fell, gathering speed with every passing century, it became something else entirely. It became a comet, and then, finally, fatally, it became an asteroid on a collision course with Earth. The impact released energy equivalent to over 100 million megatons of TNT. The explosion was so powerful that it vaporized the asteroid itself, along with billions of tons of seawater and limestone bedrock. A column of superheated rock and debris punched through the atmosphere and into space, spreading across the globe in an expanding curtain of molten glass. Wildfires ignited across entire continents. The sky turned black with soot and sulfur. Temperatures plummeted, and within a geological eye blink, perhaps as little as a few thousand years, 75% of all species on Earth had vanished forever. This is the story we know. The asteroid that killed the dinosaurs, the cosmic accident that cleared the evolutionary stage for the rise of mammals, for primates, for the unlikely ape that would eventually call itself human and begin asking questions about the universe that spawned it. But what we often fail to ask, what scientists are only now beginning to understand, is why that asteroid was there in the first place. What force could have dislodged a frozen mountain from its stable orbit in the outer solar system and sent it plunging toward Earth? What invisible hand reached across billions of kilometers of empty space and signed the death warrant for the dinosaurs? The answer lies not in the physics of comets or asteroids, not in the chaotic dynamics of the solar system's formation, but somewhere far larger and far stranger. The answer lies in the Milky Way itself, the vast rotating pinwheel of 400 billion stars that we call home. It lies in the fact that our sun, for all its apparent stability, is not fixed in place. It is moving. It is falling. And every 30 million years or so, it carries our entire solar system through one of the most dangerous regions in the galaxy, a zone of gravitational chaos, interstellar radiation, and cosmic debris that scientists call the galactic midplane. This is the story of Earth's secret clock, a timepiece that measures not seconds or centuries, but eons, tracking the slow rhythm of our star's motion through the galaxy. It is a clock whose ticks are written not in clockwork gears, but in the fossil record, in the thin layers of iridium that mark mass extinction events, in the craters that pockmark the Moon and Mars and every rocky body in our solar system. It is, perhaps, the most important natural cycle that no one ever talks about, because it operates on timescales so vast that it makes human civilization seem like less than a heartbeat in the life of a star. And we are due for another crossing very soon. To understand this cosmic rhythm, we must first understand what the Milky Way actually looks like, not as we see it from our trapped perspective within, but as it would appear to an observer hovering far outside its luminous arms. From such a vantage point, roughly 200,000 light-years above the galactic disk, you would see a vast spiral structure roughly 100,000 light-years in diameter, containing between 200 and 400 billion individual stars along with their attendant planets, moons, asteroids and comets. You would see sweeping arms of gas and young blue stars curving outward from a dense central bulge, that bulge itself harbouring a supermassive black hole with the mass of 4 million suns. And threading through everything, dark lanes of dust and molecular gas that serve as the raw material for future stars, future solar systems, future worlds where life might one day evolve to wonder at the strange and violent universe it inhabits. But the detail that matters most for our story is the shape of this galaxy in cross-section. If you could slice the Milky Way perpendicular to its spiral arms, you would not see a perfect disk of uniform thickness. You would see something more like a fried egg, thin and flat in the outer regions, but swelling to a thick bulge near the centre. The disk itself, where our Sun resides, is roughly 1,000 light-years thick in most places, and running through the exact middle of that disk, defining its mathematical centre of mass, is an invisible surface that astronomers call the galactic plane, or more colloquially, the galactic midplane. This midplane is not merely a geometric abstraction. It is a real physical environment, distinct from the regions above and below it, with its own characteristic density of matter, its own gravitational signature, its own collection of hazards and influences. The midplane is where most of the galaxy's interstellar gas and dust concentrate, drawn there by the collective gravity of billions of stars. It is where the densest molecular clouds form, where new stars ignite in brilliant clusters, where supernova remnants sweep outward in expanding shells of radiation and high-energy particles. It is, in short, the Milky Way's most active zone, a cosmic factory floor where the raw business of stellar birth and death proceeds with maximum intensity. And the Sun, as it orbits the centre of the galaxy, does not stay at a constant distance above or below this dangerous zone. Instead, like a horse on a carousel that bobs up and down even as it circles the central pole, our star oscillates through the midplane in a slow, predictable rhythm. We rise above it, reach a maximum distance of perhaps 250 light-years, slow, stop, and then fall back. We pass through the densest part of the midplane, emerge briefly on the other side, reach our maximum southern displacement, and then fall back again. One complete oscillation, up, through, down, through, and up again, takes approximately 60 to 70 million years, depending on which models you trust and where exactly in the galactic disk you measure. 60 to 70 million years. That number should sound familiar. It is, within the uncertainties of both paleontological and astronomical measurement, remarkably close to the intervals between major mass extinction events in Earth's fossil record. And this apparent coincidence has haunted a small group of scientists for over 4 decades, ever since astronomers first began to take seriously the idea that the galactic environment might influence conditions on Earth. The story of this scientific detective work begins, appropriately enough, with a map. Not a map of the galaxy, but a map of the seafloor. In the years following World War II, the United States Navy undertook an ambitious project to chart the ocean bottoms in unprecedented detail. The military applications were obvious, submarines needed to know the terrain through which they moved, but the scientific payoffs proved equally revolutionary. As oceanographers dragged their instruments across the Atlantic seabed, they discovered something entirely unexpected. A massive underwater mountain range running down the centre of the ocean, like the spine of a snake, a range that would eventually be named the Mid-Atlantic Ridge. And at the very centre of that ridge they found something even more startling. A deep rift valley, where new seafloor was continuously being created, pushing the continents of Europe and Africa away from North and South America at a rate of a few centimetres per year. This was the crucial evidence for continental drift, the confirmation of an idea that geologists had dismissed as crackpot science for half a century. The continents were not fixed. The Earth's surface was in constant motion, driven by the slow convective churning of the mantle beneath. But the oceanographic surveys produced another discovery, one that would take longer to interpret but prove equally revolutionary in its implications. As researchers studied the layers of sediment accumulating on the seafloor, they found that certain thin bands contained unusually high concentrations of rare elements. Elements like iridium, platinum and osmium that are vanishingly scarce in Earth's crust, but relatively abundant in asteroids and comets. The most famous of these iridium layers was deposited precisely 65 million years ago, at the boundary between the Cretaceous and Paleogene periods. This was the so-called KP boundary, the geological fingerprint of the dinosaur-killing impact. The physics Nobel laureate Luis Alvarez, working with his geologist son Walter, had analysed this layer in 1980 and proposed the radical hypothesis that the dinosaurs had been wiped out by an asteroid impact, a hypothesis that was confirmed a decade later with the discovery of the buried Chicxulub crater beneath the Yucatan Peninsula. But here was the thing that nagged at researchers in the years following the Alvarez paper. The KPE boundary layer was not unique. Similar iridium anomalies, though generally smaller, appeared at other stratigraphic boundaries throughout Earth's history. The late Eocene, roughly 34 million years ago, the end of the Paleozoic, roughly 250 million years ago, several events in the Devonian, the Ordovician, the early Cambrian. The fossil record seemed to be punctuated by extinction events at intervals that were not random but periodic, as if some cosmic clock were chiming at regular intervals, each chime bringing death from the sky. In 1984, two paleontologists named David Raup and John Sepkoski published a landmark paper analysing the timing of marine extinctions over the past 250 million years. Their statistical analysis suggested that major extinction events occurred approximately every 26 million years, a periodicity that could not easily be explained by terrestrial causes like volcanism or climate change. The paper sent shockwaves through the scientific community. If extinction events were periodic, then something outside the Earth must be driving them. Some cosmic metronome must be ticking away in the darkness, sending asteroid and comet storms toward the inner solar system at predictable intervals. Within months, several groups of astronomers had proposed mechanisms to explain this apparent periodicity. The most famous was the so-called Nemesis hypothesis, which posited the existence of an unseen companion star to the Sun, a red dwarf or brown dwarf orbiting at a great distance, whose gravitational influence would periodically disturb the Oort cloud and send comets raining inward. Another proposal invoked a 10th planet, a massive world beyond the orbit of Neptune that might trigger similar effects. But the hypothesis that proved most durable, and that continues to attract serious scientific attention today, was simpler and more elegant: the galactic plane oscillation. The idea was first developed in detail by the astrophysicists Michael Rampino and Richard Stothers in the mid-1980s. They noted that the Sun's bobbing motion through the galactic midplane would periodically expose the solar system to gravitational perturbations from the dense concentrations of matter found near the galactic centre of mass. As the Sun passed through the midplane, the increased density of nearby stars, gas clouds, and dark matter would exert subtle tugs on the Oort cloud, destabilising the orbits of comets that had drifted undisturbed for billions of years. Some of these comets would fall inward, crossing the orbits of the outer planets, occasionally threading the gravitational needle that would bring them into the inner solar system, and, on rare but devastating occasions, into collision with Earth. The mathematics worked out with surprising precision. The observed period of the Sun's oscillation, roughly 60 to 70 million years for a complete cycle, corresponded to a midplane crossing every 30 to 35 million years. This was close enough to the 26 million year extinction periodicity identified by Raup and Sepkoski to be intriguing, especially given the substantial uncertainties in both the paleontological and astronomical data. And the mechanism made physical sense. The Oort cloud, that vast spherical shell of cometary bodies surrounding the solar system at distances of up to 100,000 astronomical units, was known to be loosely bound, barely held by the Sun's gravity, exquisitely sensitive to any passing perturbation. A modest increase in the local gravitational field, maintained over the millions of years required for the Sun to traverse the midplane, would be more than sufficient to shake loose millions of potential impactors. But comet showers were not the only hazard associated with midplane crossings. The galactic disk, and especially its dense central layer, is also home to far more exotic dangers. As the Sun passes through this region, it is exposed to elevated levels of cosmic radiation, high-energy particles produced by supernova, pulsar winds, and the acceleration processes that occur in the shock waves of expanding nebulae. The galactic plane is where most massive stars form, and massive stars are the ones that explode as supernovae at the ends of their brief, violent lives. A nearby supernova, within 50 or 100 light-years, could shower Earth with enough radiation to trigger mass extinctions through entirely different pathways: ozone depletion, increased mutation rates, global cooling from the nitrogen compounds produced in the upper atmosphere. And there was yet another category of threat, one that scientists had only recently begun to take seriously: dense interstellar clouds. The space between stars is not truly empty. It is filled with a tenuous gas of hydrogen and helium, with scattered dust grains, with complex organic molecules, with the ejected material from dying stars. Most of this interstellar medium is so thin that it poses no danger to anything passing through it. But in certain regions, particularly near the galactic midplane, this material can condense into vast molecular clouds. Structures containing thousands or millions of solar masses, dark and cold and utterly opaque to starlight. When the sun passes through such a cloud, and passage through at least one dense cloud is virtually inevitable during a midplane crossing, several things happen that could profoundly affect conditions on Earth. The increased density of interstellar material can compress the heliosphere, that protective bubble of solar wind that normally shields the planets from galactic cosmic rays. Dust particles from the cloud can drift inward and affect the solar radiation budget, either by scattering incoming sunlight or by accumulating on planetary surfaces and altering their albedo. And the gravitational influence of a massive cloud, acting over millions of years, can perturb the orbits of planets and asteroids in ways that are difficult to predict but potentially catastrophic. The picture that emerges from decades of research is one of startling complexity. The Sun is not an isolated island drifting through a calm and featureless void. It is a traveller on a long and dangerous road, a road that passes through zones of varying hazard, that exposes it periodically to gravitational chaos, to radiation bombardment, to physical encounters with the densest concentrations of matter in the galaxy. And every time the Sun makes its passage through the galactic midplane, a passage that takes roughly 1 to 3 million years to complete, Earth and the other planets are carried along for the ride, their biosphere subjected to stresses that can range from subtle to catastrophic. The evidence for these periodic stresses is written in stone, quite literally. The geological record preserves layers of unusual chemistry, of impact debris, of sudden changes in fossil assemblages that speak to repeated environmental crises throughout Earth's history. And while not every proposed extinction periodicity has survived rigorous statistical scrutiny, the 26 million year cycle remains controversial, with some researchers finding strong evidence for it, and others finding none at all. The basic phenomenon is beyond dispute. Mass extinctions have occurred repeatedly throughout Earth's history. Many of them correlate with known impact events, and the galactic environment provides a natural explanation for why these events might cluster in time, rather than occurring randomly. To appreciate the physical reality of this cosmic cycle, we must try to visualize the Sun's motion through the galaxy with some degree of specificity. Our star currently sits roughly 50 light-years north of the galactic midplane, having crossed through it from south to north approximately 3 million years ago. We are still in the relatively dense environment near the plane, still exposed to the elevated cosmic ray flux and increased probability of close stellar encounters that characterize this region. But we are climbing, rising away from the plane at a velocity of roughly 7 kilometers per second, heading toward our maximum northern displacement, which we will reach in approximately 30 million years. At that point, the Sun will slow, stop, and begin falling back. The entire oscillation will repeat, as it has repeated countless times throughout the Sun's 4.5 billion year history. Astronomers estimate that our star has completed somewhere between 60 and 70 complete oscillations since it formed from the gravitational collapse of an interstellar gas cloud in a region not far from where it currently resides. 60 or 70 passages through the danger zone, 60 or 70 comet showers, 60 or 70 episodes of elevated radiation, gravitational perturbation, and cosmic bombardment. And yet, here we are. Life on Earth has survived every one of these passages, has recovered from every mass extinction, has rebuilt its complexity and diversity again and again like a forest regenerating after a fire. The dinosaurs fell, but the mammals rose. The great marine reptiles vanished, but the whales eventually filled their ecological niches. Life is resilient in ways that defy easy comprehension, capable of bouncing back from catastrophes that would seem to preclude any possibility of recovery. And yet life is also fragile. A thin film of organic chemistry clinging to the surface of a small rocky world, dependent on conditions that can be disrupted by events occurring thousands of light years away. This is the essential tension at the heart of our story. The galactic environment has shaped the evolution of life on Earth in ways that we are only beginning to understand. It has pruned the tree of life repeatedly, cutting off branches that might otherwise have flourished, creating ecological vacuums that allowed new forms to radiate into unoccupied niches. Without the midplane crossing that sent the Chicxulub impactor toward Earth, the dinosaurs might never have died out. Mammals might have remained small, nocturnal, marginal creatures, forever in the shadow of their reptilian overlords. Primates might never have evolved. Humans might never have existed. And this realization carries with it an unsettling corollary. If the galactic environment has shaped our past, it will also shape our future. The same forces that cleared the stage for our evolution remain active today. The sun continues its eternal dance through the galaxy, rising and falling through the midplane, exposing us periodically to all the hazards that periodic exposure entails. The Oort cloud still surrounds us, still harbouring trillions of potential impactors, still sensitive to any gravitational nudge that might send one of them tumbling inward, and we have no ability to control any of it. The universe, it turns out, is not a safe place. The night sky that seems so peaceful, so distant, so utterly removed from our daily concerns, is in fact connected to us in the most intimate possible way. The light from those distant stars carries information about our own origins and our potential fate. The darkness between them conceals forces that have shaped every living thing on this planet, and that will continue to operate long after the last human has drawn the last breath. This is the story we're going to tell. The story of Earth's cosmic environment, of the forces that have moulded it, of the evidence that scientists have painstakingly assembled from geology and paleontology and astrophysics and statistical analysis. It is a story that spans billions of years and hundreds of light years, that connects the formation of galaxies to the extinction of dinosaurs, to the evolution of the human brain that is capable of comprehending it all. And it is a story that is not yet finished. The next chapter is being written right now, in the subtle gravitational interactions occurring at the edge of the solar system, in the cosmic rays that are even now sleeting through your body, at nearly the speed of light, in the slow and patient motion of a star that knows nothing of time. We begin our investigation in the most unlikely of places, not with telescopes pointed at the sky, but with hammers and chisels applied to the rocky cliffs of coastal Italy. For it was there, in the late 1970s, that a father-son team of scientists first discovered the physical evidence that would eventually lead to the theory of galactic mass extinctions. It was there, in a thin layer of clay no thicker than a human finger, that the death of the dinosaurs left its chemical fingerprint. And it was there that the greatest detective story in the history of science truly began. A story whose implications reach far beyond our planet, far beyond our solar system, into the vast spiral structure of the galaxy that gives us our home, and periodically tries to take it away. The cliffs near the Italian town of Gubbio rise in stacked layers of limestone, each layer representing millions of years of accumulated marine sediment. For decades, geologists had studied these formations as a record of ancient ocean conditions, of changing temperatures and sea levels, and the slow drift of continents across the face of a younger Earth. But in 1977, Walter Alvarez, a young geologist from the University of California at Berkeley, was examining the KP boundary at Gubbio when he noticed something peculiar. The boundary layer itself, the thin band of clay that separated the dinosaur-bearing rocks below from the mammal-dominated rocks above, was not ordinary sediment. It contained something that did not belong. It contained a concentration of iridium over 300 times higher than any normal terrestrial rock. Iridium is one of the rarest elements on Earth's surface, a platinum group metal with a density rivaling that of osmium. It sinks readily into planetary cores during the violent differentiation that follows a world's formation. What remains in the crust is measured in parts per trillion, trace amounts so vanishingly small that their detection requires the most sensitive analytical techniques available. Yet here, in this narrow band of Italian clay, iridium was present in concentrations that defied explanation. Walter Alvarez held the secret of the dinosaur's death in his hands, but he did not yet know how to read it. He brought the problem to his father. Luis Alvarez was not a geologist, he was a physicist, and not just any physicist, a Nobel laureate whose wartime work had helped develop the atomic bomb, and whose peacetime research had ranged from cosmic ray studies to particle physics to the analysis of the Kennedy assassination. He was 70 years old in 1977, still active, still curious, and still possessed of the rigorous analytical mind that had characterized his entire career. When his son showed him the iridium anomaly, Luis immediately grasped its significance. Iridium is rare on Earth, but it is not rare everywhere. In the primordial material from which the solar system formed, material that still composes asteroids and comets, and the undifferentiated rocks that fall to Earth as meteorites, iridium is present in much higher concentrations. If the KPG boundary contained anomalous iridium, something extraterrestrial had deposited it there. The Alvarezes assembled a team. Frank Asaro and Helen Michel, nuclear chemists at Lawrence Berkeley Laboratory, applied neutron activation analysis to samples from Gubbio and from other KPG boundary sites around the world. Denmark, New Zealand, Spain. Everywhere they looked, they found the same thing. A global layer of iridium-enriched clay marking the exact moment when the dinosaurs vanished. The evidence was inescapable. 66 million years ago, something from space had struck the Earth with enough force to blanket the entire planet in debris. In 1980, the Alvarez team published their findings in the journal Science. Their paper proposed that an asteroid roughly 10 kilometers in diameter had impacted the Earth at the KP boundary, ejecting enough dust into the atmosphere to block sunlight for months or years, collapsing photosynthesis, breaking food chains, and triggering the mass extinction that ended the age of reptiles. The hypothesis was elegant, testable, and revolutionary. It was also deeply controversial. For decades, paleontologists had debated the causes of mass extinctions, generally attributing them to gradual environmental changes, climate shifts, volcanic activity, sea level fluctuations. The idea that a single catastrophic event could wipe out dominant forms of life in a geological instant seemed almost medieval, a return to catastrophism that the uniformitarian tradition of modern geology had long since rejected. The debate that followed the Alvarez paper was fierce and often personal. Some paleontologists pointed to evidence suggesting that dinosaur diversity had been declining for millions of years before the boundary, making the impact merely the final blow to an already dying dynasty. Others questioned whether an asteroid impact could really produce the specific pattern of extinctions observed in the fossil record. Why, for instance, had the crocodilians survived while the closely related dinosaurs perished? Why had some marine species died while others flourished? The impact hypothesis explained the iridium, but did it explain the biology? The answer came a decade later, from an unlikely source. In the late 1970s, before the Alvarez paper was even published, petroleum geologists working for the Mexican national oil company Pemex had discovered an unusual subsurface structure in the northern Yucatan Peninsula. Core samples from the region showed signs of impact metamorphism, shocked quartz, glassy spherules, rocks that had been instantaneously melted and reformed. The geologists dutifully filed their reports and moved on to more commercially promising prospects. It was not until 1991 that American researchers, following leads in the geological literature, identified this structure as the smoking gun the Alvarez hypothesis required. Buried beneath a kilometre of limestone sediment centred near the fishing village of Chicxulub Puerto lay a crater 180 kilometres in diameter, the scar left by the largest known impact in the last 500 million years. The discovery of Chicxulub transformed the impact hypothesis from a controversial conjecture into established fact. Additional evidence accumulated rapidly. Tsunami deposits along the coast of the Gulf of Mexico recorded waves hundreds of meters high that had swept across the continental shelf within hours of the impact. Sites in New Jersey and along the Atlantic seaboard contained glassy tektites, droplets of molten rock that had been blasted into space and rained back down across the hemisphere. The global iridium layer could now be traced to a specific source, a specific moment, a specific catastrophe. The dinosaurs had died in a rain of fire, and the evidence was written in stone for anyone patient enough to read it. But the significance of the Alvarez discovery extended far beyond the fate of the dinosaurs. For if one asteroid impact had caused one mass extinction, the logical question immediately arose: had other impacts caused other extinctions? And if so, was there a pattern? The fossil record, as we have seen, contains 5 major mass extinctions and numerous smaller ones, spread unevenly across the last 500 million years. Were these randomly distributed, or did they cluster in some way that might suggest a common cause? The Alvarez team had opened a door, and the view through it would ultimately lead back to the structure of the galaxy itself. The first person to walk through that door was David Raup. In the early 1980s, Raup was a paleontologist at the University of Chicago, known for his innovative application of statistical methods to the fossil record. While other researchers focused on individual extinction events, Raup was interested in patterns, the mathematical regularities that might underlie the apparent chaos of evolutionary history. Working with his colleague John Sepkoski, Raup had compiled an exhaustive database of marine animal families, tracking their appearances and disappearances across geological time with unprecedented precision. This database, painstakingly assembled from thousands of published sources, represented the most complete picture of life's history ever constructed, and when Raup applied time series analysis to Sepkoski's data, he found something that no one had expected. The extinctions were periodic, not perfectly periodic, not clockwork regular, but statistically periodic, occurring at intervals that clustered around a mean value of approximately 26 million years. The last 5 major extinctions, along with several smaller ones, seemed to fall along this rhythm like beats in a cosmic metronome. Raup and Sepkoski published their findings in 1984, and the scientific world erupted in controversy once again. A periodic extinction pattern implied a periodic cause, something that repeated on a timescale of tens of millions of years with enough regularity to leave its signature in the fossil record. But what natural process could possibly operate on such a schedule? The proposals came quickly, each more speculative than the last. Perhaps the Sun had an unseen companion star, a dim red dwarf or brown dwarf in an elongated orbit that carried it through the Oort cloud every 26 million years, triggering comet showers with each passage. This hypothetical object was dubbed Nemesis, after the Greek goddess of retribution, and for a time it captured the public imagination as the Death Star lurking in our cosmic backyard. Other researchers suggested that the solar system passed through an invisible disk of dark matter during its galactic orbit, and that the gravitational influence of this dark matter periodically destabilized the outer solar system. Still others proposed that the Sun crossed the spiral arms of the Milky Way on a 26 million year cycle, encountering dense molecular clouds that could perturb cometary orbits or expose Earth to elevated radiation. But the most compelling proposal, the one that would ultimately prove most consistent with the evidence, focused not on the Sun's motion through the spiral arms, but on its motion perpendicular to the galactic plane. The Milky Way, as we have established, is not a uniform disk of stars. Its matter is concentrated in a central layer perhaps 1,000 light-years thick, with density falling off rapidly above and below this midplane. And the Sun, embedded in this structure, does not orbit at a constant height. It oscillates, rising above the plane and then falling back through it, like a ball thrown upward that must inevitably return to the ground. The period of this oscillation, as calculated from the local gravitational field, is approximately 60 to 70 million years for a complete cycle, which translates to a midplane crossing every 30 to 35 million years. The numbers did not match perfectly. 26 million years was not 30 million years, but Raup and Sepkoski's periodicity had large uncertainties, and the galactic oscillation period depended on assumptions about the local mass distribution that were themselves uncertain. Within the error bars, the two values were tantalizingly close, and unlike the hypothetical Nemesis star, which has never been found despite extensive searches, the galactic oscillation was not speculative. It was a necessary consequence of the known gravitational structure of the Milky Way. The Sun must oscillate through the midplane. The only questions were how often and what consequences those crossings might have. The person who most fully developed the galactic midplane hypothesis was the English astrophysicist Michael Rampino. Beginning in the mid-1980s, Rampino and his collaborators assembled the theoretical framework that would connect galactic dynamics to terrestrial catastrophes. Their argument proceeded in several steps. First, they established that the Sun's oscillation through the galactic midplane was real and calculable, with a half period of roughly 30 million years. Second, they demonstrated that each crossing of the midplane would bring the solar system through the region of highest gravitational perturbation, where the density of stars and giant molecular clouds is greatest, and where any objects in the Oort cloud would experience maximum destabilization. Third, they showed that this destabilization would produce comet showers lasting millions of years, dramatically increasing the flux of potential impactors through the inner solar system. And fourth, they connected these comet showers to the observed record of impact craters on Earth, which showed a weak but detectable periodicity consistent with the galactic oscillation cycle. The evidence for crater periodicity was perhaps the most controversial element of the hypothesis. Earth has preserved only about 190 confirmed impact craters, a tiny sample from which to extract statistical patterns. Many craters have been erased by erosion, subduction, or burial under sediment. Many others surely lie on the ocean floor, where the basaltic crust is too young and too quickly recycled to preserve ancient impacts. Of those that remain, only a fraction can be reliably dated. Critics argued that the apparent periodicity in the crater record was an artifact of small sample size, of dating errors, of unconscious selection bias. They pointed out that if you looked at a random scatter of points, you could often convince yourself that patterns existed where none did. The human brain is a pattern-seeking organ. It finds regularities even in static. But Rampino and his collaborators persisted, refining their analyses and incorporating new data as crater ages were revised and new structures were discovered. They found that the periodicity signal, while weak, remained consistent across multiple independent datasets. They found that the timing of well-dated large craters correlated with the timing of mass extinctions at a level significantly above chance. And they found that the periodicity in both records was consistent with the galactic oscillation cycle, within the substantial uncertainties that attend both measurements. The picture that emerged was not one of clockwork precision, but of a noisy signal buried in geological randomness, exactly what you would expect if galactic dynamics influenced but did not deterministically control the frequency of terrestrial catastrophes. To understand why the galactic midplane should be dangerous, we must venture into the realm of stellar dynamics, the physics of how stars and gas clouds move within the gravitational potential of a galaxy. This is a domain governed by numbers of inconceivable vastness, by timescales that dwarf the entire span of complex life on Earth, by distances so great that light itself requires tens of thousands of years to traverse them. And yet the processes that operate at these scales have left their traces in the rocks beneath our feet, in the chemistry of ancient seas, in the bones of vanished creatures that never knew the stars were there. The midplane of the Milky Way is, quite simply, where most of the mass is concentrated. Imagine the galaxy as seen from the side, edge-on, the way we see Andromeda from Earth. The bright central bulge gives way to a thin, luminous line extending outward on both sides, the disk of stars, gas, and dust in which the sun is embedded. This disk is not infinitely thin, but it is remarkably flat. The vertical scale height is perhaps 300 light-years for the gas and dust, somewhat larger for the older stars. Within this thin layer, matter is concentrated as if pressed by an invisible hand, held in place by the combined gravity of 100 billion stars. When the sun lies within this layer, it is surrounded by neighbours, not dangerously close neighbours, even in the densest regions of the disk. The typical distance between stars is measured in light-years, but close enough to matter gravitationally over millions of years. More importantly, the disk contains not just stars but giant molecular clouds, vast complexes of cold, dense gas that can span hundreds of light-years and contain the mass of millions of suns. These clouds are the nurseries where new stars are born, but they are also gravitational perturbers, objects massive enough to influence the orbits of anything that passes nearby. And when the solar system passes through the galactic midplane, the probability of a close encounter with such a cloud rises dramatically. Giant molecular clouds do not directly threaten Earth. They are diffuse, wispy structures, their densities vanishingly small by terrestrial standards, even in their densest cores. If the solar system were to pass through the edge of such a cloud, we might see a slight increase in interstellar dust, perhaps some enhancement in the cosmic ray flux, but nothing immediately catastrophic. The danger lies elsewhere, in the outer solar system, in that frozen reservoir of primordial debris that Oort described, and that subsequent decades of observation have confirmed. The Oort cloud is only loosely bound to the Sun. Its constituent objects orbit at such vast distances and with such slow velocities that even modest gravitational perturbations can significantly alter their trajectories. A close passage by a giant molecular cloud would not rip the Oort cloud apart, but it would stir it, nudging thousands or millions of comets onto new orbits, some of which would inevitably carry them inward toward the warmth and light of the inner solar system. This stirring is not instantaneous. The objects in the Oort cloud are so distant and move so slowly that years or decades or centuries must pass before a perturbed comet crosses the orbit of Neptune, and more time still before it reaches the inner planets. The result is not a single impact but a comet shower, an extended period of elevated bombardment lasting perhaps 1 million years, during which the rate of large impacts might increase by a factor of 10 or more. And during such a shower, the probability that at least one Chicxulub-scale impactor would strike Earth rises from remote to significant, from the background level that we live with today to a level that would leave marks in the geological record. The mathematics of this process were worked out in detail during the 1980s and 1990s by dynamicists including Jack Hills, Mark Bailey, and Piet Hutt. Their computer simulations showed that the Oort cloud acts as a kind of cosmic buffer, absorbing gravitational perturbations and releasing them slowly over time as enhanced cometary flux. The Sun's passage through the galactic midplane triggers these perturbations twice per oscillation cycle, once as the system descends into the plane, and once as it rises back out. Each triggering event produces a comet shower with a characteristic delay in duration. And when multiple passages are considered over the history of the solar system, the cumulative effect is a quasi-periodic modulation of the impact rate, with peaks occurring at intervals of roughly 30 million years. This periodicity is not exact because the perturbations are not uniform. Some midplane crossings bring the solar system near massive molecular clouds. Others do not. Some crossings occur in spiral arm regions where star formation is active and gravitational potentials are complex. Others traverse the quieter interarm regions where the disk is relatively sparse. The result is a signal that is periodic in the statistical sense, present when averaged over many cycles, but noisy on any individual crossing. This noise explains why the correlation between extinctions and galactic dynamics is not perfect, why some predicted extinction peaks do not appear in the fossil record, and why some observed extinctions seem to occur at times when no galactic trigger should have been operating. The universe is more complicated than any simple model can capture, but the underlying pattern, the periodic enhancement of danger as the solar system oscillates through the galactic midplane, appears to be real. The evidence for this pattern comes from multiple independent sources, no single one of which is conclusive, but which together form a coherent picture. The fossil record shows quasi-periodic mass extinctions. The crater record shows quasi-periodic impacts. The calculated galactic oscillation period is consistent with both. The physics of Oort cloud perturbation provides a plausible causal mechanism, and the observed distribution of giant molecular clouds in the solar neighbourhood is consistent with the hypothesis that some midplane crossings are more dangerous than others. Each piece of evidence has its skeptics, its uncertainties, its alternative interpretations. But the convergence of multiple independent lines of inquiry toward the same conclusion is precisely how science establishes confidence in theories that cannot be directly tested. There is another line of evidence, one that has received less attention than the geological record, but that may ultimately prove equally important. This evidence comes not from the rocks of Earth, but from the chemistry of the solar system, specifically from the analysis of cosmic ray exposure ages in meteorites. When a rocky body in space is exposed to the interstellar medium, the cosmic rays that pervade the galaxy leave their mark in its surface layers. Energetic protons and heavier nuclei shatter atomic nuclei in the rock, producing characteristic isotopes that can be measured in the laboratory. The longer the exposure, the greater the accumulation of these cosmogenic isotopes. And by analysing meteorites that have fallen to Earth, scientists can reconstruct the history of cosmic ray exposure throughout the solar system. This history tells an interesting story. The cosmic ray flux that the solar system experiences is not constant. It varies with the solar cycle, rising and falling over the 11-year rhythm of magnetic activity on the Sun. It varies with the passage of the solar system through interstellar space, changing as the local density of energetic particles fluctuates, and crucially, it varies with the Sun's position relative to the galactic midplane. The midplane is where cosmic ray sources, supernovae, pulsars, stellar winds from massive stars, are most abundant. The midplane is where the interstellar medium is densest, where energetic particles scatter and diffuse and accumulate. When the solar system lies near the midplane, the cosmic ray flux is enhanced. When it rises above or below, the flux diminishes. This variation has biological implications beyond the direct effects of radiation damage. Cosmic rays ionize the upper atmosphere, producing chemical species that would not otherwise exist in significant quantities. They influence cloud formation by providing nucleation sites for water droplets. They affect the transparency of the atmosphere to solar radiation. Some researchers have proposed that variations in cosmic ray flux, driven by the galactic oscillation, have influenced Earth's climate over geological time, not as the primary driver of temperature change, but as a modulating factor that enhances or suppresses the effects of other climate forcings. The evidence for this hypothesis remains contested, with some studies finding significant correlations and others finding none. But the underlying physics is sound. Cosmic rays do affect atmospheric chemistry, and the galactic oscillation does affect cosmic ray flux. Whether the magnitude of these effects is large enough to leave a detectable signal in the climate record is a question that remains open. What is not open to question is the reality of the galactic environment itself. The Milky Way is a dynamic system, constantly evolving, constantly changing, and the solar system is embedded within it in ways that matter for life on Earth. The peaceful night sky that greets us when we step outside is an illusion of distance, a consequence of our tiny perspective on processes that span millions of light years and billions of years. The same processes that built the stars and scattered the elements that compose our bodies continue to operate today, shaping our environment in ways we're only beginning to understand. We have traced the evidence from the cliffs of Gubbio to the craters of the Yucatan, from the databases of paleontology to the simulations of celestial mechanics. We have seen how a thin layer of iridium-enriched clay led to the discovery of Chicxulub, how the periodicity of extinctions led to theories of galactic dynamics, how the oscillation of the Sun through the midplane provides a framework for understanding the pattern of catastrophes that have punctuated the history of life. But our story is far from complete. The galactic environment affects Earth in ways that go beyond comet showers and asteroid impacts, ways that involve the very radiation that enables life to exist, and that, in excess, can snuff it out. The cosmic rays that even now are passing through your body, that are ionizing atoms in your cells and damaging your DNA, are a constant reminder that the universe is not a gentle place, and when the Sun approaches the galactic midplane, when we enter the regions where those rays are most intense, the biological effects become impossible to ignore. The cosmic ray environment near the galactic midplane is not merely denser, it is qualitatively different. The energy spectrum shifts, the composition changes, the biological consequences multiply in ways that simple flux measurements cannot capture. To understand why, we must first understand what cosmic rays actually are. The term itself is a misnomer, a relic of the early 20th century when physicists first detected this mysterious radiation streaming down from space and assumed, reasonably enough, that it consisted of electromagnetic waves similar to X-rays or gamma rays. We now know that cosmic rays are not rays at all, but particles, protons, helium nuclei, heavier ions stripped of their electrons, and a smattering of electrons and positrons. These particles travel at velocities approaching the speed of light, carrying energies that dwarf anything achievable in terrestrial particle accelerators. A single cosmic ray proton can pack the kinetic energy of a baseball thrown at major league speeds, all concentrated in a particle far smaller than an atom. The origins of these particles are as violent as their energies suggest. When a massive star exhausts its nuclear fuel and collapses into a supernova, the resulting shockwave does not simply expand and dissipate. It accelerates charged particles through a process called diffusive shock acceleration, bouncing them back and forth across the expanding shock front, each crossing adding to their energy. Over thousands of years, a single supernova remnant can accelerate particles to millions of times the energies produced in the Large Hadron Collider. These particles then escape into interstellar space, where magnetic fields scramble their trajectories, erasing any directional memory of their origin. They diffuse through the galaxy like smoke through a room, filling interstellar space with a persistent background of high-energy radiation. But not all regions of the galaxy are equally filled. The supernova remnants that produce cosmic rays are concentrated in the galactic midplane, where massive stars are born and die. The magnetic fields that confine and scatter cosmic rays are strongest in the midplane, where the interstellar medium is densest. The result is a cosmic ray distribution that peaks near the galactic centre and near the midplane, diminishing as one moves outward or upward into the halo regions above and below the disk. The solar system, as it oscillates through this distribution, experiences significant variations in cosmic ray exposure, variations that correlate with its position relative to the midplane. The magnitude of this variation has been estimated through multiple methods, none of them precise, all of them consistent in their general conclusions. When the solar system lies within the densest regions of the midplane, cosmic ray flux may increase by a factor of 2 or more compared to its values at maximum displacement above or below. This might seem modest, but cosmic ray effects are often nonlinear. A twofold increase in flux can produce more than a twofold increase in certain biological and atmospheric effects, because the damage mechanisms involve cascades and chain reactions that amplify the initial energy deposition. When a high-energy cosmic ray enters Earth's atmosphere, it does not simply travel to the surface and stop. It collides with an atmospheric nucleus, nitrogen or oxygen typically, and shatters it into a spray of secondary particles. These secondaries then collide with other nuclei, producing still more particles in a branching cascade that can contain millions of individual particles by the time it reaches ground level. This is called an extensive air shower, and it is the primary means by which cosmic rays interact with the terrestrial environment. The secondary particles include pions, muons, neutrons, and gamma rays, each with its own biological effects. Muons are particularly penetrating. They pass through meters of rock and can reach deep underground, depositing energy along their tracks. Neutrons are particularly dangerous biologically. They scatter off hydrogen atoms in tissue, producing recoil protons that ionize densely along short paths, causing clustered DNA damage that is difficult for cellular repair mechanisms to fix. The cumulative effect of cosmic ray exposure on biological systems has been studied extensively, driven in part by concerns about astronaut health, and in part by interest in radiation effects on Earth. The results are sobering. Cosmic rays are responsible for a measurable fraction of the natural background radiation that all living things receive. This fraction is small at sea level. Cosmic rays contribute roughly 10% of average background exposure, but it increases with altitude and latitude. At the cruising altitude of commercial aircraft, cosmic ray exposure is several hundred times higher than at sea level. Airline crews receive radiation doses comparable to nuclear industry workers, and this is under normal conditions, with the solar system near its current position relative to the midplane. What would happen if cosmic ray flux doubled? The direct increase in radiation exposure would be modest in absolute terms, perhaps an additional fraction of a millisievert per year for individuals at sea level, more for those at high altitude. But radiation damage is cumulative, and the effects compound over generations. DNA mutations accumulate in germ cells, the eggs and sperm that carry genetic information to the next generation. Most mutations are neutral or harmful. Natural selection weeds out the harmful ones over time, but at a cost in reduced fitness and increased mortality. An increase in mutation rate shifts this balance, increasing the genetic load on populations, potentially reducing reproductive success, potentially driving vulnerable species toward extinction. This effect would be most pronounced in populations already under stress. A species struggling with habitat loss, food scarcity, or changing climate might be tipped over the edge by an increase in genetic damage. The extinction would appear to have purely ecological causes, because the radiation increase would leave no obvious trace. Only by looking at the timing, by noticing that the extinction coincided with a midplane crossing, would the connection become apparent, and even then the causal chain would be difficult to prove because radiation effects are inherently statistical. Not every individual is affected equally. Luck plays an enormous role in which cells are struck by cosmic rays and where the damage occurs. But there is another pathway through which cosmic rays affect the biosphere, one that operates not through direct radiation damage, but through atmospheric chemistry and climate. This pathway involves the production of ionization in the upper atmosphere, the formation of chemically reactive species, and the influence of those species on processes ranging from cloud formation to ozone depletion. The physics is well established. The magnitude of the effects remains controversial. When cosmic rays ionize the atmosphere, they produce free electrons and positive ions that quickly react with surrounding molecules. In the stratosphere, these reactions can produce nitrogen oxides, compounds that catalytically destroy ozone. Ozone depletion increases the flux of ultraviolet radiation reaching Earth's surface, with effects on ecosystems ranging from increased skin cancer in humans to reduced photosynthesis in phytoplankton. The sensitivity of ozone to cosmic ray variations has been modelled extensively, with results suggesting that the variations associated with galactic oscillation could produce measurable but not catastrophic changes in UV flux, perhaps a few % increase during midplane crossings. A few % increase might seem insignificant, but ultraviolet radiation is highly damaging to biological molecules, particularly DNA and proteins. Organisms have evolved extensive protective mechanisms: pigmentation, DNA repair enzymes, behavioural avoidance of direct sunlight, but these mechanisms have limits. Coral reefs, which exist in shallow sunlit waters, are particularly vulnerable to UV damage. So are phytoplankton, the microscopic photosynthesizers that form the base of marine food webs. A sustained increase in UV flux could reduce primary productivity in the oceans, with cascading effects up the food chain. Combined with other stresses, ocean acidification, temperature changes, altered nutrient availability, UV damage could contribute to marine extinctions without leaving any direct fossil evidence. The cloud formation pathway is even more intriguing and even more uncertain. Cosmic rays produce ions in the lower atmosphere, not just the stratosphere, and these ions can influence the formation of cloud condensation nuclei, the tiny particles around which water droplets form. Without adequate condensation nuclei, water vapour remains gaseous even when supersaturated. With abundant nuclei, clouds form more readily. Changes in cloud cover affect Earth's albedo, the fraction of incoming sunlight reflected back to space, which in turn affects global temperature. More clouds mean higher albedo, meaning more reflection, meaning lower temperatures. Fewer clouds mean the opposite. The idea that cosmic rays might influence climate through cloud formation was proposed in the 1990s by Danish physicist Henrik Svensmark and has been debated vigorously ever since. Laboratory experiments have confirmed that ionization can indeed promote the formation of aerosol particles, but the magnitude of this effect under atmospheric conditions remains uncertain. Satellite observations have searched for correlations between cosmic ray flux and cloud cover, with mixed results. Some studies finding significant correlations, others finding none, still others finding correlations that disappear when additional variables are controlled for. The scientific community remains divided, with some researchers convinced that cosmic ray cloud coupling is real and climatologically significant, others equally convinced that it is negligible, and many in between, waiting for more definitive evidence. What all sides agree on is that the effect, if it exists at all, would be small compared to other climate forcings: greenhouse gases, orbital variations, volcanic activity. Cosmic ray cloud coupling is not a replacement for established climate science. It is at most a modulating factor that might enhance or suppress trends driven by other mechanisms. But over geological time, even small modulations can have large consequences. A slight enhancement of cooling during an ice age, a slight suppression of warming during an interglacial, repeated over millions of years, could shift the statistical distribution of climate states in ways that affect the biosphere. Species that thrive in one climate regime and struggle in another would feel these shifts in their ranges, their abundances, their evolutionary trajectories. The galactic oscillation provides a natural experiment for testing these ideas. If cosmic ray climate coupling is real and significant, we would expect to see climate variations correlated with the Sun's position relative to the midplane. If the effect is negligible, we would expect no such correlation. The geological record contains proxies for past climate: oxygen isotope ratios in marine sediments, pollen assemblages in terrestrial deposits, the distribution of climate-sensitive organisms through time, and these proxies can be compared to models of the galactic oscillation. Several research groups have attempted such comparisons, with results that remain frustratingly ambiguous. Some studies find significant correlations, others find that apparent correlations disappear when the analysis is refined or when different statistical methods are applied. Part of the difficulty lies in the limitations of the geological record itself. Climate proxies are noisy, affected by local factors as well as global ones, subject to preservation biases and dating uncertainties. The galactic oscillation models are also uncertain, dependent on assumptions about the structure of the Milky Way and the properties of the solar system's orbit. When two uncertain time series are compared, it is easy to find correlations that are not real or to miscorrelations that are present. The signal-to-noise ratio is low, and the risk of confirmation bias, seeing patterns because you expect to see them, is high. But even if cosmic ray climate coupling proves to be negligible, the galactic oscillation affects Earth's environment in other ways that are better established. The gravitational perturbation of the Oort cloud during midplane crossings is one such effect, as we have already discussed. Another involves encounters with giant molecular clouds, not the interstellar clouds of diffuse gas that the solar system routinely traverses, but denser, more massive structures that pose their own distinct hazards. Giant molecular clouds are the birthplaces of stars. They are vast accumulations of cold hydrogen and helium, laced with dust and complex molecules, dense enough to shield their interiors from the disruptive radiation of nearby stars, dense enough to collapse under their own gravity, and fragment into the clumps that become protostars. These clouds are concentrated in the spiral arms of the Milky Way, and in the galactic midplane, where gas density is highest. They range in size from a few light-years across to hundreds of light-years, in mass from a few hundred solar masses to millions. When the solar system passes near or through a giant molecular cloud, several things happen. The gravitational influence of the cloud perturbs the orbits of Oort cloud comets, potentially triggering comet showers more intense than those produced by ordinary midplane crossings. The enhanced density of interstellar gas increases the drag on the solar wind, compressing the heliosphere and exposing the inner solar system to particles that would normally be deflected. The dust associated with the cloud can enter the solar system, altering the zodiacal light, potentially reaching the inner planets, affecting atmospheric chemistry in ways that depend on the composition of the dust. The probability of such encounters is not negligible. The solar system passes through the galactic midplane roughly every 35 million years, and the midplane contains numerous giant molecular clouds. Estimates suggest that close encounters, passages within a few parsecs of a cloud center, occur every 100 to 200 million years, with direct passages through cloud material occurring less frequently. Each encounter would last a few million years, long enough for the accumulated effects to leave geological traces. Some researchers have proposed that past giant molecular cloud encounters coincide with major extinction events, providing an alternative or complementary explanation to the comet shower hypothesis. The increased cosmic ray flux, the compressed heliosphere, the influx of interstellar dust, the gravitational perturbation of the Oort cloud, all of these effects would peak simultaneously during a cloud encounter, creating a period of sustained environmental stress that could push ecosystems over the edge. The Permian extinction, the greatest mass dying in Earth's history, has been tentatively linked to such an encounter, though the evidence remains speculative. The timing is plausible, the mechanism is plausible, but proving a causal connection across 250 million years of geological history is extraordinarily difficult. What makes the giant molecular cloud hypothesis attractive to some researchers is that it provides a mechanism for sustained environmental stress, as opposed to the instantaneous catastrophe of an impact event. Impacts are bad, but they are brief. The Chicxulub impactor struck and was done in minutes. The environmental consequences played out over years to decades. A giant molecular cloud encounter, by contrast, would persist for millions of years, maintaining elevated cosmic ray flux and perturbed cometary orbits throughout that entire interval. This sustained stress might explain extinction patterns that show prolonged decline rather than sudden collapse, patterns that do not fit the impact model well but might fit the cloud encounter model better. The interplay between these different mechanisms, impacts, comet showers, cosmic ray exposure, cloud encounters, is complex and poorly understood. They are not mutually exclusive. All of them are real, all of them operate, and their effects might reinforce or cancel each other, depending on the timing and the circumstances. A midplane crossing that does not include a giant molecular cloud encounter might produce only modest environmental stress. One that does might produce catastrophic consequences. A comet shower that coincides with elevated cosmic ray flux might be more damaging than either factor alone, because organisms already stressed by radiation damage would be less able to cope with the ecological disruption of multiple impacts. This complexity is both frustrating and fascinating. It means that simple periodic models of extinction, the kind that predict catastrophes every 35 million years like clockwork, are almost certainly wrong in detail, even if they capture something real about the long-term rhythm of life and death on Earth. The actual pattern is probably stochastic, driven by the occasional confluence of multiple stress factors rather than by any single periodic mechanism. The periodicity observed in the extinction record may reflect an underlying rhythm of galactic oscillation, modulated by the random timing of cloud encounters and the chaotic dynamics of cometary orbits. This perspective has implications for how we think about the future as well as the past. If extinction risk is driven by the confluence of multiple factors, then predicting future catastrophes requires understanding not just the galactic oscillation, but also the current distribution of giant molecular clouds, the current state of the Oort cloud, and the current configuration of gravitational perturbations from passing stars. All of these factors are, in principle, measurable. The Gaia Space Telescope is mapping the positions and velocities of billions of stars, allowing astronomers to identify nearby stars that will pass close to the Sun in the coming millions of years. Radio telescopes are mapping the distribution of molecular clouds in the solar neighbourhood, providing data on potential future encounters. Models of the Oort cloud are becoming more sophisticated, incorporating better physics and better data on the galactic environment. The picture that emerges from this work is cautiously reassuring. No known giant molecular cloud lies directly in the Sun's path for the next several million years. No known star will pass close enough to severely perturb the Oort cloud in the near astronomical future. The Sun is currently rising through the galactic midplane, having crossed from below roughly 3 million years ago, and will continue rising for the next several million years before reaching its maximum displacement and beginning its descent again. This means we're entering a period of relatively reduced cosmic ray flux, reduced gravitational perturbation, reduced environmental stress from galactic factors. But cautious reassurance is not certainty. The catalogues of nearby stars and molecular clouds are incomplete. The dynamics of the Oort cloud are poorly constrained. The models of galactic structure contain significant uncertainties. And even if we knew the galactic environment perfectly, we would still face the inherent unpredictability of chaotic systems. A comet nudged onto an Earth-crossing orbit today might not arrive for millions of years. Predicting its trajectory that far in advance is fundamentally impossible. What we can say with confidence is that Earth exists within a dynamic galactic environment, one that has shaped the history of life and will continue to shape its future. The cosmic rays passing through you as you listen to these words are a reminder of that environment. The thin layer of iridium in the cliffs of Gubbio is a reminder. The craters that pockmark the faces of the Moon and Mars are reminders. We live within a story that spans billions of years and millions of light years. A story in which the peaceful stability of our daily experience is a temporary calm within a larger pattern of punctuated catastrophe. The Sun continues its eternal dance through the galaxy, rising and falling through the midplane, carrying its family of planets and comets and dust through an ocean of stars and gas and radiation. Earth continues its orbit around the Sun, spinning on its tilted axis, its biosphere responding to the subtle and not-so-subtle changes in its cosmic environment. And life continues its endless experiment, adapting and evolving and occasionally dying back in great waves of extinction that clear the stage for new evolutionary experiments. This is the context in which we must understand the history of mass extinctions. It is not enough to look at the immediate causes, the impactors, the volcanism, the climate changes. We must also look at the underlying drivers, the galactic factors that set the stage for catastrophe by filling the inner solar system with potentially hazardous objects and bathing Earth in elevated radiation. The Chicxulub impactor was the proximate cause of the end Cretaceous extinction, but the comet or asteroid that became Chicxulub may have been placed on its fatal trajectory by gravitational perturbations ultimately traceable to the galactic oscillation. The chain of causation stretches backward in time and outward in space, connecting the death of the dinosaurs to the structure of the Milky Way itself. The structure of the Milky Way itself. Those words carry a weight that grows heavier the longer you contemplate them. We speak of the galaxy as if it were a fixed backdrop, a celestial canvas against which the drama of Earth unfolds. But the galaxy is not a stage. It is an actor. Its spiral arms churn with newborn stars and the expanding remnants of dead ones. Its central bar rotates, slowly shifting the gravitational landscape across hundreds of millions of years. Its dark matter halo, invisible and enigmatic, tugs at every star and gas cloud, shaping orbits in ways we're only beginning to understand. And through all of this, the midplane pulses with its own complex rhythm, a zone where matter concentrates, where energy flows, where the difference between safety and catastrophe can be measured in mere light years. To truly grasp what happens when the Sun crosses the galactic midplane, we must first understand what the midplane actually is. Not in the abstract terms of astronomy textbooks, but in concrete, physical terms that illuminate why this seemingly arbitrary geometric feature carries such profound consequences for life on Earth. Imagine yourself floating in interstellar space, somewhere within the disk of the Milky Way. You're surrounded by stars in every direction, but not uniformly. If you look toward what astronomers call the galactic plane, you see a river of light stretching across your field of view, the combined glow of billions of stars that lie close to the galaxy's central disk. This is the same band of light visible from Earth on clear, dark nights, the feature that gave the Milky Way its name. But what you're seeing is not just stars. Woven among those distant suns are vast clouds of gas and dust, some illuminated by nearby stars into spectacular nebulae, others dark and cold, visible only as shadows against the stellar background. These clouds are not randomly distributed. They congregate toward the mid-plane, drawn there by the same gravitational forces that confine the stars themselves. The mid-plane is, in essence, the galaxy's waistline. Just as Earth's atmosphere is thickest at sea level and thins with altitude, the Milky Way's gas and dust are thickest at the midplane, and thin as you move above or below it. The scale, however, is almost incomprehensibly vast. The disk of the Milky Way spans roughly 100,000 light-years in diameter, but its thickness, the vertical extent of the region where matter concentrates, is only about 1,000 light-years. This makes the disk remarkably thin relative to its width, like a cosmic pancake stretched across a quarter of the visible universe. The midplane runs through the centre of this pancake, a zone perhaps 200 light-years thick where the density of matter reaches its maximum. Within this narrow band, the concentration of molecular clouds is several times higher than in the regions above and below. The stellar density is also elevated, though not as dramatically as the gas density. Most significantly, the gravitational potential, the combined pull of all this concentrated matter, is substantially stronger at the midplane than elsewhere in the disk. This gravitational gradient is what causes the Sun to oscillate, rising and falling through the midplane like a buoy bobbing in slow motion through an ocean of dark matter and stars. The physics of this oscillation emerges from a beautiful piece of gravitational dynamics, first worked out in detail by astronomers in the 20th century. Consider the Sun's motion perpendicular to the galactic plane. When the Sun is below the midplane, the mass concentrated above it exerts a net gravitational pull upward. This pull accelerates the Sun toward the midplane. As the Sun crosses the midplane and rises above it, the mass now concentrated below exerts a net gravitational pull downward. This pull decelerates the Sun's upward motion, eventually bringing it to a halt at some maximum displacement above the midplane. Then the Sun begins falling back toward the midplane, accelerating as it goes, passing through the midplane with maximum velocity, overshooting into the region below, decelerating, stopping, and beginning the cycle again. This is simple harmonic motion, the same physics that governs a pendulum or a mass on a spring. The period of the oscillation depends on the distribution of matter in the galactic disk, specifically on how the gravitational potential changes with distance from the midplane. Early estimates, based on incomplete knowledge of the galaxy's structure, suggested periods ranging from 60 to 90 million years. Modern analyses, incorporating data from stellar surveys and dynamical models, have narrowed this range considerably. The current best estimates place the oscillation period between 60 and 70 million years, with most studies favouring values around 64 to 66 million years. This number carries profound implications. If the oscillation period is approximately 65 million years, then the Sun crosses the midplane roughly every 32 million years, once heading upward, once heading downward, completing a full cycle. And 32 million years is strikingly close to the periodicity that researchers have identified in various geological and biological records. The extinction cycles, the impact cratering cycles, the episodes of enhanced cosmic ray flux all seem to pulse at intervals that hover around 30 million years. The correspondence is too close to be easily dismissed as coincidence, yet not precise enough to constitute proof of causation. The difficulty lies in measuring both the galactic oscillation period and the terrestrial periodicities with sufficient accuracy to determine whether they genuinely match. Each measurement carries substantial uncertainty. The oscillation period depends on the mass distribution in the galactic disk, which is not directly observable and must be inferred from the motions of stars and gas clouds. The terrestrial periodicities depend on the ages assigned to extinction events, impact craters, and geological boundaries, which are derived from radiometric dating techniques with their own sources of error. When you compare two uncertain numbers and find that they approximately match, you cannot be certain whether the match is real or merely an artifact of the uncertainties. This is why the debate over galactic drivers of extinction has persisted for decades without definitive resolution. The evidence is suggestive but not conclusive. The patterns are tantalizing but not quite clear enough to compel universal acceptance. And underlying all the technical uncertainties is a deeper question. Even if the periodicities match, how would we demonstrate the causal mechanism? What physical evidence would prove that midplane crossings actually produce the biological consequences that researchers have proposed? One approach to this problem involves looking not just at whether events occur periodically, but at whether they occur at the right times. If we could determine exactly when the Sun crosses the midplane and compare those moments to the ages of mass extinctions, we might find a compelling correspondence that goes beyond mere periodicity. The Sun's current position and velocity relative to the midplane are reasonably well known from astronomical observations. From these we can extrapolate backward in time, calculating when past midplane crossings should have occurred. The extrapolation becomes increasingly uncertain as we go further back. The Sun's velocity changes slightly with each perturbation from passing stars and molecular clouds. But for the past few 100 million years, the estimates are probably reliable within 10 million years or so. When researchers perform this extrapolation, they find that the Sun should have crossed the midplane roughly 33 million years ago, 65 million years ago, 97 million years ago, and so on, marching backward at intervals of approximately 32 million years. The correspondence with major extinction events is intriguing. 33 million years ago falls close to the Eocene-Oligocene boundary, a time of significant faunal turnover in the fossil record. 65 million years ago is, of course, the end Cretaceous extinction, the demise of the dinosaurs. 97 million years ago lies within the mid-Cretaceous, a period of elevated extinction rates that has received less attention than the boundary events, but shows clear signals of biological stress. But intriguing correspondence is not proof. The uncertainties in both the astronomical extrapolation and the geological dating are large enough that coincidental alignment cannot be ruled out. A skeptic could point out that mass extinctions have occurred at many times throughout Earth's history, and some of them will inevitably fall close to calculated midplane crossing times simply by chance. To distinguish genuine causation from coincidental timing, we would need either much more precise dating of both the astronomical and geological events, or independent evidence of the physical mechanisms through which midplane crossings affect Earth. This is where the cosmic ray evidence becomes particularly important. Unlike cometary impacts, which leave discrete traces at specific moments in time, cosmic ray bombardment produces continuous effects that can be measured through proxies spanning millions of years. The beryllium-10 records, the iron-60 detections, the cosmogenic nuclide variations in meteorites, all provide windows into the history of cosmic ray exposure that can be compared against the predicted timing of midplane crossings. If cosmic ray flux genuinely increases near the midplane, and if we can measure this flux variation through geological proxies, we have an independent test of the galactic hypothesis that does not depend on the uncertain timing of discrete extinction events. The evidence from cosmogenic nuclides is, like so much else in this field, suggestive but not definitive. Some studies have found variations in isotope ratios that appear to correlate with the predicted galactic oscillation cycle. Others have failed to find such correlations, or have found correlations with different periodicities. The interpretation of the data depends heavily on the models used to convert isotope ratios into cosmic ray flux, and different models can yield different conclusions. The field remains active, with new data and new analytical techniques continually refining our understanding. Perhaps the most compelling piece of physical evidence linking cosmic rays to biological and geological processes comes not from the ancient past, but from direct observation of the present. cosmic rays striking Earth's atmosphere trigger complex cascades of secondary particles, some of which reach the surface and contribute to background radiation. But the atmospheric effects extend beyond simple radiation exposure. When high-energy cosmic rays collide with nitrogen and oxygen molecules in the upper atmosphere, they initiate chemical reactions that produce nitrogen oxides. These nitrogen oxides catalyze the destruction of ozone, the molecule that shields Earth's surface from harmful ultraviolet radiation. During periods of elevated cosmic ray flux, ozone depletion could expose surface life to increased UV damage, adding to the biological stress from direct radiation exposure. Atmospheric physicists have modelled these effects in considerable detail, calculating how much ozone depletion would result from various levels of cosmic ray enhancement. The results suggest that during galactic midplane crossings, when cosmic ray flux might increase by a factor of 2 or 3, ozone levels could drop by 10 to 20%. This is comparable to the ozone depletion caused by human chlorofluorocarbon emissions in the late 20th century, significant enough to cause measurable increases in UV-related health effects, but not so severe as to cause immediate ecological collapse. Over millions of years, however, even modest increases in UV exposure could affect mutation rates, alter ecosystem dynamics, and contribute to the selective pressures that drive evolution. The cloud formation hypothesis adds another layer to this picture. Henrik Svensmark and his collaborators have proposed that cosmic rays influence climate by promoting the formation of cloud condensation nuclei in the lower atmosphere. The mechanism involves the ionization of air molecules by cosmic rays, which then cluster into aerosol particles that can seed cloud droplets. If this effect is significant, increased cosmic ray flux during midplane crossings could produce increased cloud cover, which in turn could cool the planet by reflecting more sunlight back into space. Some researchers have argued that this cosmic ray climate connection could explain ice ages and other climate variations observed in the geological record. The cloud formation hypothesis remains controversial. Laboratory experiments have confirmed that ionization can indeed promote aerosol formation under certain conditions. But whether this effect is significant in the real atmosphere, with its complex mix of particles, humidity, and air currents, is still debated. Climate models that include cosmic ray effects have produced mixed results, with some showing significant climate sensitivity to cosmic ray variations, and others showing negligible effects. The hypothesis has attracted both enthusiastic supporters and skeptical critics, and the scientific community has not reached consensus on its validity. What emerges from all these lines of evidence, the comet showers, the cosmic ray variations, the ozone depletion, the climate effects, is a picture of the galactic midplane crossing as a time of heightened environmental stress on multiple fronts. No single mechanism may be sufficient to cause a mass extinction, but the combination of several mechanisms acting together could push ecosystems toward collapse. A modest increase in cometary impacts, combined with elevated radiation exposure, combined with ozone depletion, combined with climate instability, could create conditions in which species already stressed by other factors, continental drift, sea level changes, volcanic activity, find themselves pushed past the breaking point. This concept of multiple stresses acting in concert is crucial to understanding the complexity of mass extinction events. Paleontologists have long recognized that the major extinctions were not simple, single-cause catastrophes. The end Cretaceous event, for example, occurred against a backdrop of massive volcanism in India, where the Deccan traps were pouring out enormous quantities of lava and volcanic gases. Sea levels were changing, climate was unstable, many species were already in decline before Chicxulub struck. The impactor may have been the final blow, the coup de grace that finished off ecosystems already weakened by other stresses. And those other stresses may themselves have been partly driven by galactic factors, creating a cascade of causation that stretches from the spiral arms of the Milky Way to the extinction of individual species on Earth. The pattern becomes even more complex when we consider the time delays inherent in the galactic mechanisms. A comet perturbed from the Oort cloud during a midplane crossing may not reach the inner solar system for millions of years. Cosmic rays elevated during the crossing continue bombarding Earth as the Sun rises away from the midplane. Climate effects initiated during the crossing may persist or even intensify, as feedback loops amplify the initial perturbation. This means that the biological effects of a midplane crossing could be spread over millions of years, beginning before the geometric moment of crossing and continuing long afterward. The relationship between galactic position and extinction timing is not simple cause and effect, but a complex interplay of delayed, overlapping and interacting influences. This temporal complexity helps explain why the search for clear periodicity in the extinction record has proven so frustrating. If mid-plane crossings triggered instantaneous catastrophes, we would expect to see sharp extinction peaks at regular intervals, easily identifiable in the fossil record. But if the effects are spread over millions of years, overlapping and interacting with other geological and biological processes, the periodic signal would be smeared out, harder to detect, more easily obscured by noise. The statistical analyses that have sought to identify this signal face the challenge of extracting a weak smeared periodic pattern from a noisy, incomplete record of extinction intensities. Yet the signal does seem to be there, hovering just at the edge of statistical significance, tantalizing researchers with its persistence across multiple independent analyses. The roughly 30 million year periodicity appears in extinction data, in impact cratering data, in geological boundary events. Different researchers using different methods find patterns that broadly agree. The consilience of evidence, the convergence of multiple independent lines of inquiry on similar conclusions, gives confidence that something real underlies the observed patterns, even if we cannot yet specify that something with precision. The galactic perspective also illuminates the deep interconnection between Earth and its cosmic environment in ways that go beyond mere catastrophism. The elements that compose our bodies were forged in stars, distributed through interstellar space by supernova explosions and stellar winds, concentrated in molecular clouds, and eventually incorporated into the solar nebula from which the Sun and planets formed. The water in Earth's oceans may have been delivered by comets from the Oort cloud, water that formed in the cold outer reaches of the protosolar disk from interstellar ice grains. The carbon in our DNA, the calcium in our bones, the iron in our blood, all trace back to nucleosynthesis in stellar cores, dispersal through the galaxy, and concentration in the particular region of the Milky Way where our solar system happened to form. We are, quite literally, products of galactic evolution. Our existence depends not just on the local conditions of Earth's surface, but on the large-scale history and structure of the galaxy itself. The midplane oscillation is one aspect of this dependence, perhaps the most dramatic in its potential for catastrophic influence, but certainly not the only connection between terrestrial life and galactic dynamics. Every element we use, every photon of sunlight that powers our biosphere, every gravitational tug that keeps Earth in its stable orbit, all arise from processes that span millions of light years and billions of years. This perspective challenges our intuitive sense of Earth as an isolated sphere, self-contained and self-sufficient, responding only to internal processes and perhaps the gravitational influence of the Sun and Moon. Earth is not isolated. It is embedded in a galactic environment that continuously shapes its conditions, sometimes gently and sometimes violently. The relative calm of the present moment is a product of our current galactic location, rising away from the midplane into a region of reduced matter density and reduced perturbation. This calm is temporary. In 15 or 20 million years, the Sun will reach the apex of its oscillation and begin descending again toward the midplane. In 30 million years, we will be back in the zone of maximum stress, where cosmic ray flux peaks and Oort cloud perturbation intensifies. 30 million years seems impossibly remote from the perspective of human lifetimes, or even human civilizations. But from the perspective of geological and biological time, it is imminent. 30 million years ago, the first apes were just beginning to diverge from other primates. 30 million years from now, who knows what descendants of current life will inhabit the Earth, or whether any descendants will exist at all. The galactic oscillation operates on timescales that dwarf human experience, but match perfectly with the timescales of evolution and extinction. It is a rhythm that life has danced to for 4 billion years, rising and falling through the midplane, facing periodic challenges that cull the weak and reward the adaptable. Understanding this rhythm is more than an academic exercise. It speaks to fundamental questions about the nature of life in the universe, the probability of intelligence arising on other worlds, and the long-term future of life on Earth. If midplane crossings genuinely trigger mass extinctions, then we must consider their implications for the habitability of planets throughout the galaxy. The Sun's oscillation amplitude and period are not unique. They reflect the general dynamics of stars within the galactic disk. All stars oscillate, rising and falling through the midplane on timescales determined by their orbital velocities and the local mass distribution. This means that any planet orbiting a disk star will experience similar periodic variations in its cosmic environment. The roughly 30 million year cycle is not specific to our solar system, but a general feature of galactic dynamics in this region of the Milky Way. Planets throughout the galactic disk face the same periodic stress that Earth faces, the same elevated cosmic ray flux, the same gravitational perturbation of cometary reservoirs. If these stresses suppress the emergence or persistence of complex life, then the habitability of galactic disk planets may be systematically lower than we might otherwise expect. Conversely, if midplane crossings drive evolution by periodically disrupting ecosystems and creating opportunities for innovation, they may be necessary features of the environments that produce intelligent life. The Chicxulub impact, as devastating as it was for the dinosaurs, cleared ecological niches that allowed mammals to diversify and eventually produce primates and hominids. Without that catastrophe, intelligence might never have arisen on Earth, or might have arisen in a completely different lineage, with consequences for the history of life and technology that we cannot imagine. The galactic oscillation, through its periodic delivery of impactors and radiation, may be not just a threat to life, but an essential component of the evolutionary process that ultimately generates complexity and intelligence. These speculations venture beyond what current evidence can support, but they illustrate the broader significance of understanding the galactic influences on terrestrial life. This is not merely a matter of cataloguing past catastrophes or predicting future ones. It is a matter of understanding our place in the cosmos, the conditions that made our existence possible, and the factors that will shape the future of life on Earth and perhaps elsewhere in the galaxy. The data continue to accumulate. The Gaia mission maps stars with unprecedented precision, revealing the detailed structure of the galactic disk and allowing better models of the gravitational potential that drives the solar oscillation. Astronomers discover new molecular clouds in the solar neighbourhood, refining our picture of the interstellar environment through which the Sun travels. Paleontologists date extinction events with increasing accuracy, tightening the constraints on periodicity claims. Each new measurement narrows the uncertainties, bringing us closer to a definitive understanding of whether and how galactic factors influence life on Earth. The answer matters. It matters for our understanding of Earth's history, for our assessment of future risks, for our search for life elsewhere in the universe. The dance of the Sun through the galactic midplane is not an abstract astronomical curiosity, but a fundamental feature of the environment in which we exist. The pattern of mass extinctions that punctuates the fossil record may be its signature, written in the rocks of Earth, but composed in the gravitational dynamics of the Milky Way. The evidence, when assembled with care, tells a story that stretches across scales almost too vast to comprehend. From the microscopic crystals of iridium preserved in boundary clays to the sweeping arc of 100 billion stars rotating around a common centre, the threads connect in ways that challenge our intuitions about cause and effect. We are accustomed to thinking of Earth as isolated, a blue marble floating in the void, its history determined by internal processes and perhaps the occasional cosmic accident. The galactic perspective reveals something different, a planet embedded in a dynamic environment, subject to forces that operate on timescales far longer than human civilization, but far shorter than the age of life itself. Consider what it means to exist in such an environment. Every moment Earth moves through space at tremendous velocity, not just orbiting the Sun at 30 kilometers per second, not just following the Sun around the galactic centre at 230 kilometers per second, but also oscillating perpendicular to the galactic plane at velocities that, though modest by comparison, carry profound consequences over millions of years. At this moment, as you listen to these words, the Sun is climbing upward, away from the midplane, carrying the entire solar system through a relatively sparse region of the galaxy. The cosmic ray flux at Earth's surface is lower than it was 30,000 years ago. The Oort cloud feels less gravitational stress than it did when our ancestors huddled in caves during the last ice age. We exist in a moment of relative cosmic calm, a valley between peaks of galactic influence. But the climb will eventually slow. The gravitational pull of the mass concentrated near the midplane will decelerate the solar system's vertical motion, bring it to a halt, and then draw it back downward. sometime in the next 15 to 20 million years, a span of time beyond meaningful human comprehension, but a mere heartbeat in geological terms, the Sun will pass through the galactic midplane once again. When it does, Earth will face the same elevated risks that have shaped its history repeatedly over the past 4 billion years. Increased cosmic radiation, gravitational perturbation of the Oort cloud, potential passage through dense interstellar material. Whether these risks translate into actual catastrophe depends on factors we cannot predict. The precise location of molecular clouds at that future time, the random distribution of cometary orbits, the resilience of whatever ecosystems exist on Earth millions of years hence. This uncertainty does not diminish the importance of understanding the phenomenon. If anything, it highlights the value of the scientific work now underway. Every improvement in our knowledge of galactic structure, every refinement of our models of the solar system's motion, every new fossil that helps date ancient extinction events, all of these contribute to a clearer picture of the risks Earth faces and the factors that have shaped its past. The goal is not prediction with certainty, but understanding with humility. The cosmos operates on scales that dwarf human concerns, but those scales intersect with our existence in ways that matter profoundly. The question of whether the periodicity claimed by Raup and Sepkoski and their successors represents a genuine signal or a statistical artifact remains contested. But the debate itself has been enormously productive. It has forced paleontologists to develop more rigorous methods for dating extinction events and quantifying their severity. It has pushed astronomers to build better models of the galactic gravitational potential and the solar system's trajectory through it. It has inspired geologists to search for physical evidence of cosmic impacts and their environmental effects with unprecedented thoroughness. Even if the final verdict on the 26 or 30 million year cycle proves negative, the scientific progress stimulated by the hypothesis will have been valuable in itself. But the accumulating evidence suggests that the final verdict will be more nuanced than simple confirmation or rejection. The picture that emerges from decades of research is one of genuine galactic influence, operating through multiple pathways: cosmic ray modulation, cometary perturbation, interstellar cloud encounters, but with effects that are probabilistic rather than deterministic, and that interact with internal Earth processes in complex ways. The galactic oscillation does not cause mass extinctions in any simple causal sense. Rather, it modulates the background probability of catastrophic events, creating windows of elevated risk that may or may not coincide with actual catastrophes, depending on circumstances that involve considerable randomness. A comet nudge from the Oort cloud by gravitational perturbation during a midplane crossing may strike Earth, or it may be ejected from the solar system, or it may be captured into a distant orbit that keeps it harmless for billions of years. The elevated cosmic ray flux during a midplane crossing may coincide with other factors that amplify its effects on climate and ecosystems, or it may occur during a period of geological stability that buffers against disruption. The galactic rhythm provides a framework for understanding extinction patterns, but the details depend on contingencies that no model can fully capture. This probabilistic interpretation may seem unsatisfying to those who seek definitive answers, but it reflects the genuine complexity of the natural world. The history of life on Earth has been shaped by countless factors operating across all scales of space and time, from the movement of individual molecules within cells to the gravitational dynamics of galactic spiral arms. No single factor explains everything. The galactic oscillation takes its place among volcanism, plate tectonics, asteroid impacts, ocean circulation, atmospheric chemistry, and evolutionary dynamics as one of the many influences that have shaped the trajectory of life. Its distinctive feature is its cosmic origin, its connection to processes far beyond the boundaries of the solar system. In that sense, it provides a reminder that Earth is not isolated, that the planet's history cannot be understood without reference to its galactic context. The practical implications of this understanding extend beyond pure science into questions of planetary defense and long-term planning. Humanity has recently begun to take seriously the threat posed by asteroid and comet impacts, developing detection systems and contemplating deflection technologies that might protect Earth from catastrophic collisions. The galactic perspective suggests that these efforts, while valuable, address only part of the picture. Cometary impacts are not random events uniformly distributed in time, but cluster during periods of Oort cloud perturbation, periods that may be predictable. at least in a statistical sense, based on our knowledge of the solar system's galactic trajectory. If we survive long enough as a technological civilization, this knowledge could inform resource allocation for planetary defense, concentrating vigilance and capability during the periods of elevated risk associated with midplane crossings. Similarly, the cosmic ray connection suggests avenues for monitoring and possibly mitigating environmental risks. We cannot shield the entire planet from galactic cosmic rays, but we might monitor their flux with sufficient precision to anticipate periods of elevated exposure. We might develop more detailed models of how cosmic ray variations affect atmospheric chemistry, cloud formation, and climate, allowing better prediction of the environmental consequences of galactic influences. We might even, in the distant future, consider technological interventions that modify Earth's magnetic field or atmosphere to buffer against cosmic ray variations. These possibilities lie far beyond current capabilities, but they represent the kind of long-term thinking that understanding galactic influences might inspire. The search for life elsewhere in the galaxy also benefits from this perspective. When astronomers evaluate the habitability of exoplanets, they typically focus on factors like stellar luminosity, planetary distance from the host star, atmospheric composition, and the presence of liquid water. These factors are undoubtedly important, but they represent only part of the habitability equation. A planet might have perfect conditions by all these measures and still be hostile to the development of complex life if it exists in a region of the galaxy where cosmic ray flux is persistently high or where dense molecular clouds frequently disrupt planetary climates. Conversely, a planet in a quieter galactic neighbourhood might maintain conditions conducive to life over longer timescales, increasing the probability that evolution produces complexity and intelligence. The galactic habitable zone, as some researchers have termed it, represents an attempt to incorporate these considerations into assessments of planetary habitability. The concept suggests that not all regions of the galaxy are equally hospitable to life, even holding constant the properties of individual planetary systems. The galactic centre, with its high stellar density and intense radiation environment, may be systematically hostile to life. The outer regions of the galaxy, while quieter, may lack the heavy elements necessary for rocky planet formation and complex chemistry. The intermediate zone where the Sun resides may represent a galactic sweet spot, combining adequate heavy elements with moderate cosmic ray flux and reasonable intervals between catastrophic perturbations. But even within this zone, the oscillation through the midplane creates periodic challenges that complex life must survive. The implications for the prevalence of intelligent life in the universe are profound. If midplane crossings and their associated stresses suppress the emergence of complexity on most galactic disk planets, then the galaxy may be a lonelier place than optimistic estimates suggest. The Drake equation, the famous formula for estimating the number of communicating civilizations in the galaxy, includes a term for the fraction of planets on which life develops, and another for the fraction on which intelligence arises. The galactic oscillation might affect both terms, suppressing life on planets subject to frequent catastrophic disruption and limiting intelligence to the rare worlds that survive long enough for evolution to produce it. Alternatively, if midplane crossings serve as evolutionary accelerators, pruning old lineages and creating opportunities for innovation, they might actually increase the probability of intelligence arising, but only on planets that survive the periodic culling. Either way, the galactic context matters for estimating the prevalence of life and intelligence throughout the cosmos. These considerations also bear on the famous Fermi paradox, the puzzle of why we have not detected evidence of extraterrestrial intelligence, despite the apparent high probability that such intelligence exists. Many proposed solutions to the paradox invoke factors that limit the prevalence or longevity of technological civilizations, self-destruction through warfare or environmental degradation, the difficulty of interstellar communication or travel, the possibility that intelligent life takes forms we cannot recognize. The galactic oscillation suggests another possibility, that civilizations, like species, face periodic catastrophic risks that most fail to survive. A civilization that develops during a period of cosmic calm might flourish for millions of years before a midplane crossing unleashes a cometary shower or radiation pulse that ends its existence. The galaxy might be littered with the ruins of civilizations that failed to anticipate or survive the periodic challenges imposed by galactic dynamics. If this hypothesis has any merit, it implies something important for our own civilization. We are the product of a specific evolutionary history shaped by galactic factors we're only beginning to understand. Our survival, on timescales of millions of years rather than centuries, depends in part on forces that operate far beyond our planet, even beyond our solar system. The cosmic perspective is not merely a source of wonder or philosophical reflection, but a practical necessity for a civilization that aspires to long-term survival. Understanding the galactic oscillation and its consequences is part of the larger project of understanding our environment, an environment that extends far beyond the atmosphere of Earth. The astronomers who mapped the Milky Way with early telescopes could not have imagined that their work would eventually connect to questions of biological evolution and species survival. The paleontologists who catalogued fossil shells in Italian limestones did not know that the patterns they observed might reflect the dynamics of 100 billion stars rotating around a distant centre. The physicists who developed cosmic ray detectors for basic research in particle physics did not anticipate that their instruments would provide data relevant to understanding mass extinctions. Yet all these strands weave together into a narrative that spans disciplines and scales, revealing connections that become visible only when viewed from sufficient height. This is the nature of scientific progress. Isolated investigations that seem unrelated prove to be aspects of larger patterns, and understanding advances through synthesis as much as analysis. The Gaia spacecraft, orbiting the Sun at a stable gravitational point far from Earth, embodies this synthetic ambition. Its mission is to map the positions and motions of more than 1 billion stars with unprecedented precision, creating a three-dimensional model of the Milky Way that previous generations could only dream of. The data it produces allow astronomers to trace the Sun's trajectory through the galaxy with new accuracy, refining estimates of oscillation period and amplitude. They reveal the detailed structure of the disk, its warps and ripples, its spiral arms and stellar streams, its distribution of mass that determines the gravitational potential through which the Sun moves. Gaia has already transformed our understanding of galactic dynamics, and its data will continue to yield insights for decades as researchers develop new methods for extracting information from its vast catalogues. Among Gaia's discoveries are perturbations in the galactic disk apparently caused by past interactions with satellite galaxies, dwarf galaxies that orbit the Milky Way and occasionally pass through its disk, sending ripples through the stellar distribution like stones dropped in a pond. These interactions add complexity to the picture of galactic dynamics that underlies the oscillation hypothesis. The disk through which the Sun oscillates is not static but evolving, its structure modified by ongoing gravitational interactions with satellite galaxies and perhaps by other processes we do not yet fully understand. The oscillation period and amplitude may have varied over the age of the solar system as the disk's properties changed. The neat picture of a regular 30 million year cycle may be an approximation to a more complex reality in which the periodicity drifts and fluctuates over hundreds of millions of years. This complexity does not invalidate the hypothesis of galactic influence on terrestrial life. It enriches it. A truly accurate model of the Sun's galactic trajectory must incorporate not just the smooth, background potential of the disk, but also the perturbations caused by satellite galaxy interactions, the non-axis symmetric structure of spiral arms, the gravitational influence of individual molecular clouds that happen to pass near the solar system. Building such a model requires the integration of data from many sources: Gaia's stellar positions and velocities, radio observations of molecular clouds, infrared surveys of stellar populations, cosmological simulations of galaxy formation and evolution. The project is ongoing, and each year brings new refinements and new surprises. Among the surprises has been the discovery that the solar system's trajectory through the galaxy is more complex than simple oscillation through a symmetric disk. The Milky Way's disk is not perfectly flat, but warped and flared, particularly in its outer regions. The gravitational potential that governs stellar motions is not axially symmetric, but features spiral arms, bars, and other structures that create non-circular motions. The Sun's orbit around the galactic centre is not perfectly circular, but slightly elliptical, with radial oscillations that carry it closer to and farther from the galactic centre on timescales of hundreds of millions of years. All these complexities affect the vertical oscillation through the midplane, modulating its period and amplitude in ways that researchers are only beginning to understand. The practical consequence is that attempts to match the timing of past midplane crossings with dated extinction events must account for uncertainties in galactic dynamics, as well as uncertainties in paleontological chronology. The error bars on both sides of the comparison are substantial, and claims of precise correlation must be viewed with appropriate skepticism. What the data support is not a clockwork mechanism that triggers extinctions at exact intervals, but a statistical tendency for elevated extinction risk during periods associated with midplane proximity. This is sufficient to establish the reality of galactic influence on terrestrial life while acknowledging the limitations of current knowledge. The researchers who work in this field understand these limitations better than anyone. They have spent careers developing the techniques necessary to extract reliable signals from noisy data, to distinguish genuine patterns from statistical artifacts, to integrate knowledge from disciplines that rarely communicate. Their caution about strong claims reflects hard-won experience with the pitfalls of interdisciplinary research, where assumptions valid in one field may not apply in another, and where confirmation bias can lead investigators astray. The hypothesis of galactic influence on mass extinctions has survived decades of scrutiny, not by generating definitive proof, but by consistently motivating productive research and generating testable predictions that data have not refuted. The next phase of research promises new tests and new constraints. Ground-based observatories using adaptive optics and interferometry achieve spatial resolution that rivals or exceeds space-based telescopes, allowing detailed studies of nearby molecular clouds and their interactions with the solar system's extended structures. New paleontological databases compile extinction data from around the world, allowing statistical analyses with larger sample sizes and finer temporal resolution than ever before. Numerical simulations of galactic dynamics achieve new levels of sophistication, incorporating effects that earlier models neglected and revealing behaviours that data alone cannot yet distinguish. The synthesis of these advances may finally settle the question of whether the galactic oscillation leaves a detectable imprint on the history of terrestrial life, or whether the pattern that Raup and Sepkoski glimpsed remains forever ambiguous. Whatever the outcome, the investigation will have transformed our understanding of Earth's place in the cosmos. The planet we inhabit exists not in isolation, but as part of a vast galactic ecosystem, subject to influences that originate light years away and operate over millions of years. The fossils beneath our feet preserve a record that extends beyond terrestrial processes to encode information about the dynamics of the Milky Way itself. The extinction events that punctuate the history of life may represent not random catastrophes, but the predictable consequences of the sun's eternal dance through the galactic midplane. And so, we arrive at the present moment, at this particular instant in the sun's long journey through the galaxy, at this precise location in the eternal oscillation that has shaped the history of life on Earth. The solar system currently resides approximately 50 light-years north of the galactic midplane, moving upward through the disk at a velocity of roughly 7 kilometers per second. We are in the ascending phase of our oscillation, climbing away from the dense central regions toward the relative emptiness of the northern galactic halo. By the most recent calculations, the last midplane crossing occurred between 1 and 3 million years ago, during the geological epoch known as the Pliocene or early Pleistocene, a time that witnessed the emergence of the genus Homo and the beginning of the ice ages that would shape human evolution. The timing is suggestive, but far from definitive. The Pliocene-Pleistocene transition was indeed marked by significant environmental changes: the onset of northern hemisphere glaciation, the closure of the Central American Seaway, shifts in ocean circulation and atmospheric carbon dioxide. Whether any of these changes can be attributed to the solar system's passage through the galactic midplane remains an open question. The climate fluctuations of the ice ages appear driven primarily by Milankovitch cycles, the periodic variations in Earth's orbital parameters that modulate the distribution of solar radiation across seasons and latitudes. But the underlying sensitivity of the climate system to these orbital forcings may itself depend on factors influenced by galactic position, factors like cosmic ray flux and cloud formation that remain subjects of active research and vigorous debate. What is clear is that we live in an interglacial period of a glaciated planet, a brief warm interval in an ongoing ice age that began approximately 2.6 million years ago. The glacial cycles that have characterized this period, the advance and retreat of ice sheets over 100,000-year timescales, and have driven the evolution of countless species, including our own. Homo sapiens emerged during the Middle Pleistocene, perhaps 300,000 years ago, and spread across the globe during a series of glacial and interglacial episodes that repeatedly transformed landscapes and ecosystems. The cognitive and cultural capabilities that allowed our ancestors to survive these environmental challenges, the capacity for abstract thought, complex language, technological innovation, social cooperation, may owe something to the galactic context in which they evolved. The cosmic ray flux during midplane passages, the enhanced mutation rates that some researchers propose, the environmental stresses that drove adaptive innovation, all these factors may have contributed to the crucible in which human consciousness emerged. This is speculation, of course, the kind of grand narrative synthesis that scientists approach with caution and philosophers embrace with enthusiasm. The evidence is suggestive rather than conclusive, the connections plausible rather than proven. But the speculation illuminates something profound about the human condition. Our existence as thinking beings depends on a chain of cosmic circumstances that stretches back through billions of years and extends outward across thousands of light years. The atoms in our bodies were forged in stellar cores and supernova explosions. The planet we inhabit coalesced from the debris of an ancient molecular cloud. The evolutionary pressures that shaped our lineage included influences from beyond the solar system, from the galactic environment through which we perpetually travel. We're not merely terrestrial creatures, but galactic beings, our origins and our fate bound up with the dynamics of the Milky Way itself. Looking forward, we can ask when the next significant galactic event might affect the solar system, and what form that effect might take. The current upward motion through the disk will carry us higher into the northern galactic halo over the next 30 million years or so, reaching a maximum displacement of perhaps 200 to 300 light-years above the midplane before gravitational attraction reverses our motion and begins the long fall back toward the dense central regions. During this ascending phase, the cosmic ray flux should gradually decrease as we move away from the concentration of supernova remnants and cosmic ray accelerators near the midplane. The frequency of encounters with dense molecular clouds should similarly decline, reducing the probability of gravitational perturbations to the Oort cloud and the comet showers that might follow. In principle, this means the coming tens of millions of years should be relatively quiet from a galactic perspective, a period of reduced cosmic ray bombardment and diminished cometary threat. The extinction risks associated with midplane passages should be at their minimum during this ascending phase, creating a window of relative safety for whatever biosphere exists on Earth during this interval. Of course, this calculation ignores the many other hazards that life faces: asteroid impacts from sources other than the Oort cloud, volcanic catastrophes, climate shifts driven by terrestrial processes, and ultimately the slow brightening of the sun that will render Earth uninhabitable within a billion years or so, regardless of galactic dynamics. The galactic oscillation is one factor among many, significant but not dominant, a modulation of risk rather than its primary driver. The next midplane crossing will occur approximately 30 million years in the future, give or take the substantial uncertainties in galactic dynamics. The species that inhabit Earth at that time, if any, will face enhanced extinction risk as the solar system plunges through the dense central regions of the disk. Whether those species will include descendants of humanity is a question that depends on choices being made today and in the coming centuries. Will human civilization survive its current technological adolescence, with its nuclear weapons and climate disruption and ecological devastation? Will our descendants spread beyond Earth to other worlds in the solar system, reducing the existential risk posed by any single planetary catastrophe? Will they develop the capacity for interstellar travel, escaping entirely the gravitational bonds of the Sun and choosing their own path through the galaxy rather than following the predetermined orbit we currently ride? These questions seem remote from the concerns of daily life, from the mundane struggles and small triumphs that occupy human attention in the present moment. Yet they are the questions that matter most when viewed from the cosmic perspective that this investigation has opened. The galactic oscillation that may have contributed to past mass extinctions operates on timescales that dwarf individual human lives and even the entire span of recorded history. The 30 million years until the next midplane crossing is roughly 10,000 times longer than the 3,000 years of written civilization, roughly 100,000 times longer than a single human lifetime. From our vantage point, such durations are effectively infinite. geological eternities that exceed our capacity for intuitive comprehension. But the fossil record teaches that life persists across such timescales, that lineages endure through catastrophes and adaptations and evolutionary transformations that produce beings unimaginably different from their ancestors. The mammals that survived the end Cretaceous extinction were small, marginal creatures, ecologically subordinate to the dinosaurs that had dominated for over 150 million years. Yet from those humble survivors descended the whales and elephants, the bats and primates, the entire magnificent diversity of mammalian life, including the species now capable of contemplating its own cosmic context. Evolution has no foresight, no plan, no guarantee of continued success, but it has demonstrated a remarkable capacity for generating novelty and complexity in response to changing conditions, for finding solutions to problems that did not previously exist, for producing forms of life that could not have been predicted from first principles. The next 30 million years will witness evolutionary changes as profound as those that separated the Cretaceous mammals from their present-day descendants. The biosphere of Earth 30 million years hence will be populated by creatures as different from today's species as we are from the small shrew-like mammals that scurried in the shadows of Tyrannosaurus. Whether any of those future beings will possess consciousness, technology, the capacity to understand their own situation, these are questions beyond our ability to answer. What we can say with confidence is that the galactic context will continue to shape the history of life on whatever planet supports it, that the oscillation through the midplane will continue to modulate extinction risk and evolutionary opportunity, that the cosmic environment will remain an active participant in the drama of terrestrial biology. The researchers who have dedicated their careers to understanding these connections have given us something precious, a glimpse of Earth's place in the larger cosmic order, a recognition that the planet is not a closed system but an open one, subject to influences from across the galaxy. Their work continues in observatories and laboratories around the world, in computer simulations and paleontological digs, in the careful accumulation of evidence that gradually constrains theories and refines understanding. They do not claim to have solved the mystery of mass extinctions, or to have proven the galactic hypothesis beyond reasonable doubt. They claim only to have advanced the investigation, to have established the physical plausibility of galactic influence, and identified the mechanisms through which such influence might operate. The final verdict awaits future discoveries. New crater dates, new extinction chronologies, new constraints on galactic dynamics, new theoretical insights that may transform the field in ways we cannot anticipate. What emerges from this long investigation is not a simple answer, but a profound reorientation of perspective. The Earth we inhabit, the biosphere of which we are part, the evolutionary history that produced us, all these exist within a cosmic context that extends far beyond the Sun and its planets. The Milky Way is not merely a backdrop for human affairs, a pretty spiral pattern glimpsed on dark nights away from city lights. It is the environment in which the solar system moves, the source of influences that have shaped the history of life, the galactic ecosystem of which Earth is one small component. The oscillation through the midplane that we have traced across this investigation connects the largest scales of cosmic structure to the most intimate details of biological evolution. It links the dynamics of spiral arms and dark matter halos to the extinction of trilobites and dinosaurs, the formation of molecular clouds to the emergence of new evolutionary lineages, the explosion of distant supernovae to the mutation rates in cells billions of years later. This is the universe that science reveals, a cosmos of intricate interconnections across scales of space and time that exceed human intuition, a web of causation that links the very large to the very small in ways that challenge our capacity for comprehension. The investigation of galactic influence on terrestrial life is one thread in that web, one pathway through the labyrinth of cosmic relationships that constitute physical reality. Following that thread has led us through stellar dynamics and evolutionary biology, through crater chronology and cosmic ray physics, through the technical details of data analysis and the grand questions of life's meaning and fate. The journey has not reached a final destination, scientific investigations never do, but it has opened vistas that previous generations could not have imagined. The scientists who first proposed the link between galactic oscillation and mass extinctions worked with primitive tools by current standards, limited computing power, sparse extinction databases, crude models of galactic dynamics. Yet they glimpse something real, a pattern in the data that has survived decades of increasingly sophisticated analysis. The pattern remains controversial, its interpretation contested, its implications uncertain. But it has proven generative, motivating research programs that have advanced knowledge in multiple disciplines regardless of whether the original hypothesis ultimately proves correct. This is the way science often works. Bold conjectures that may be wrong in detail but right in spirit, that point toward truths that subsequent investigations refine and sometimes transform beyond recognition. David Raup and Jack Sepkoski began this journey with a simple question about the timing of mass extinctions, a question that led them into statistical territory where few paleontologists had ventured. Richard Stothers and Michael Rampino extended the investigation into astrophysics, proposing mechanisms that connected terrestrial catastrophes to cosmic causes. Matisse and Whitman, Hills, and countless others contributed pieces to an emerging picture of Earth as a galactic traveller, subject to periodic hazards that originate in the structure of the Milky Way itself. The researchers who continue this work today inherit a rich tradition of interdisciplinary inquiry, a body of evidence and theory that provides the foundation for future advances. They know that the questions they pursue may not be answered in their lifetimes, that the full picture may require centuries of additional research to complete. They pursue those questions anyway, driven by the same curiosity that has animated scientific inquiry since humans first looked up at the stars and wondered what they were. The stars are suns, we now know, nuclear furnaces that illuminate planets we're only beginning to detect and characterize. Some of those planets may harbor life, may have witnessed their own evolutionary dramas shaped by the same galactic influences that have affected Earth. The Milky Way contains hundreds of billions of stars, many with planetary systems, distributed across a disk that all of them traverse through their own vertical oscillations. The pattern we have traced for the solar system applies in modified form to every stellar system in the galaxy. All of them bob through the midplane, all of them experience varying exposure to cosmic rays and molecular clouds. All of them face the hazards and opportunities that galactic dynamics creates. If life is common in the universe, then the influence of galactic structure on biological evolution is not a peculiarity of Earth, but a general feature of life throughout the Milky Way, and presumably throughout the cosmos. This thought carries us to the edge of speculation, to the boundary between science and philosophy, where evidence grows thin and imagination takes over. But it is a thought worth entertaining, a possibility worth contemplating as we consider our place in the cosmic order. The same forces that shaped our evolutionary past operate throughout the galaxy, creating conditions that may have fostered the emergence of life and mind on countless other worlds. The same oscillation that brought comet showers and extinction events to Earth may have punctuated the history of life on planets orbiting distant stars, may have shaped evolutionary trajectories that led to conscious beings asking the same questions we ask. We may not be alone in wondering about the galaxy's influence on life, that wondering may be happening right now, across thousands of light years, among beings whose existence we can only imagine. Or we may be unique, the only minds in a vast and empty galaxy, the sole inheritors of a cosmic accident that produced consciousness once, and only once in the Milky Way's 12 billion-year history. The evidence does not yet distinguish between these possibilities, does not tell us whether the universe is teeming with life or essentially dead except for this one improbable exception. What the evidence does tell us is that life on Earth is ancient and resilient, that it has survived catastrophes that would seem to render survival impossible, that it has found ways to persist through mass extinctions and ice ages and impacts that sterilize the surface to depths of hundreds of meters. Life is tenacious, adaptable, creative in its solutions to the challenges that environments pose. If it exists elsewhere, and the chemistry of the universe suggests that it might, it probably shares these qualities, probably has evolved its own strategies for surviving the hazards that galactic dynamics creates. The oscillation continues. The sun rises and falls through the galactic disk in its eternal rhythm, carrying its family of planets through regions of varying density and danger. The pattern that began before Earth existed will continue long after the sun exhausts its nuclear fuel and expands into a red giant that engulfs the inner solar system. The galaxy itself will persist for billions of years more, until its eventual merger with the Andromeda Galaxy creates a new elliptical system in which the concept of a disk and a midplane may no longer apply. On timescales even longer than these, the universe itself will undergo transformations that current physics can only dimly foresee. The accelerating expansion driven by dark energy, the eventual heat death as entropy reaches its maximum, the fates of matter and energy in an aging cosmos. Against this backdrop of cosmic impermanence, the investigation we have undertaken assumes a different character. It becomes not merely an exercise in understanding the past, but an act of bearing witness to the present, a recognition that we exist at a particular moment in a vast temporal sweep that extends billions of years in both directions. The consciousness that allows us to contemplate these matters is itself a product of the processes we have examined. The stellar nuclear synthesis that created the elements, the planetary formation that produced Earth, the biological evolution that generated nervous systems capable of abstract thought, the galactic dynamics that modulated extinction risk and shaped evolutionary trajectories. We are the universe examining itself, matter organised in patterns complex enough to wonder about their own origins and fate. The midplane crossing that occurred a few million years ago coincided roughly with the emergence of our lineage, with the appearance of beings who would eventually develop the capacity to understand the cosmic context of their existence. This may be coincidence, one of countless patterns that the human mind discovers in complex data, more a reflection of our pattern-seeking nature than of any genuine connection. Or it may be significant, a clue to something deeper about the relationship between cosmic events and evolutionary innovation. The enhanced cosmic ray flux during midplane passages, the increased mutation rates that some researchers propose, the environmental stresses that drove adaptive responses, perhaps these factors did contribute to the emergence of human consciousness, did help create the conditions in which big brains and complex cultures could evolve. We cannot know for certain. The evidence is too fragmentary, the timescales too vast, the confounding factors too numerous to permit confident conclusions. What we can know is that we are here, now, at this moment in the sun's galactic journey, possessed of minds capable of reconstructing the past and imagining the future. We are the beneficiaries of 4 billion years of evolutionary experimentation, the inheritors of genetic information that has survived countless catastrophes and adaptations. We carry within us the molecular memories of bacteria that lived before Earth had oxygen in its atmosphere, of fish that first crawled onto land, of mammals that survived the asteroid impact that ended the dinosaurs' reign. Our existence is the sum of all the extinctions we avoided, all the catastrophes our ancestors survived, all the evolutionary innovations that accumulated across geological time to produce creatures capable of reading these words and contemplating their meaning. The galactic oscillation that has shaped this history will continue shaping whatever future unfolds. The species that exist 30 million years from now, when the solar system next crosses the galactic midplane, will face the same elevated risks that periodically threatened their ancestors. They may not survive, extinction is the fate of most species eventually, or they may evolve into forms unrecognizable to us, adapted to conditions we cannot imagine. If they possess consciousness and curiosity, they may reconstruct the history we have examined here, may understand their own existence as the product of cosmic forces operating across scales of space and time, that humble individual experience. They may look back at this moment, at the early 21st century when humans first began to grasp their galactic context, and see it as a turning point, the beginning of an awareness that would transform their civilization's relationship with the cosmos. The sun continues its journey, carrying Earth and its passengers through the vast darkness between the stars. Above the galactic plane now, climbing toward the apex of its oscillation, the solar system traverses a region of relative calm. Lower cosmic ray flux, fewer molecular clouds, diminished cometary threat. The 30 million years of this ascending phase stretch before us, an interval that exceeds by orders of magnitude any timescale that human plans typically encompass. What we do with this time, how we use this window of relative safety, will determine whether conscious observers exist to witness the next midplane crossing, or whether Earth returns to a world of microbes and invertebrates, the brief experiment with intelligence having failed. The choice is ours, and the stakes could not be higher. The cosmos has given us a rare gift, a planet capable of supporting complex life, a galactic position currently favourable to that life's persistence, a moment of technological capability when we might extend our presence beyond this single, vulnerable world. What we make of this gift remains to be seen. The oscillation continues, indifferent to our choices, marking time in millions of years while we measure our lives in decades. The pattern is set, the physics determined, but within those constraints, possibilities remain open, futures remain undecided, outcomes depend on actions yet to be taken. Somewhere in the uncharted depths of space, a comet that will not reach the inner solar system for another 50 million years drifts in cold silence, its orbit a relic of perturbations imparted during a midplane crossing that occurred before dinosaurs walked the Earth. Somewhere in the fossil record, evidence of extinctions we have not yet recognized preserves the signature of cosmic catastrophes whose dates remain to be determined. Somewhere in the galaxy, the processes that created us continue operating, generating new stars and planets, new molecular clouds and cosmic rays, new possibilities for life and mind throughout the disk. The story we have traced is not complete, stories never are, but it has revealed something essential about our place in the cosmic order, about the threads that connect the dynamics of galaxies to the evolution of life on planets orbiting ordinary stars. The galactic midplane lies 50 light-years below us now, invisible from our vantage point but as real as the ground beneath our feet. We are rising away from it, bound on a journey that will take us to the edge of the disk and back again, over and over, for as long as the sun exists to make the trip. This is our inheritance, our cosmic circumstance, the context within which all human achievements and failures must ultimately be understood. We are not the centre of the universe, not the purpose for which creation was designed, not the endpoint of evolution's striving. We are passengers on a small rocky world orbiting an ordinary star, riding the gravitational currents of a galaxy that contains hundreds of billions of other stars, embedded in a universe that may contain hundreds of billions of other galaxies. And yet we are also the universe looking back at itself, matter organised in patterns complex enough to contemplate its own origins, beings capable of tracing the cosmic influences that shaped our existence. This capacity for understanding does not make us central or important in any cosmic sense, but it makes us participants in the universe's ongoing story, active agents in a drama whose scope exceeds anything we can fully comprehend. The oscillation through the galactic midplane that we have examined is one movement in that drama, one rhythm in the vast symphony of cosmic evolution that has played for billions of years and will play for billions more. We have heard that rhythm, have felt its influence in the pattern of mass extinctions and evolutionary innovations that constitute the history of life. We have understood something of its mechanics, traced its consequences, contemplated its future implications. This understanding is our contribution to the cosmic story, our small addition to the universe's growing self-awareness. It will persist in whatever form human knowledge takes in the future, in books and databases, in educational traditions and scientific theories, in the memories of beings who may no longer be recognizably human, but who will carry forward the insights their ancestors achieved. The galaxy does not care about our understanding, feels no gratification at being comprehended, operates according to physical laws that are indifferent to whether conscious observers exist to appreciate them. But we care. We find meaning in understanding, purpose in inquiry, satisfaction in the hard-won knowledge that connects our brief lives to the vast sweep of cosmic time. The dance continues, the eternal oscillation of stars through a galactic disk that formed 12 billion years ago and will persist for billions of years to come. The music plays on, inaudible to human ears but written in the fossil record, encoded in crater chronologies, detectable in the statistical patterns of extinction and origination that punctuate the history of life. We have learned to hear that music, to read its notation, to understand something of the composer's methods. The performance is not finished, will never be finished as long as stars orbit galactic centres and planets harbour life. But we have been privileged to attend, to listen, to appreciate something of the grandeur and terror and beauty of the cosmic symphony, in which our existence is one brief and precious note. The sun rises through the galactic plane, carrying everything we have ever known toward a destiny we cannot foresee, and the story goes on.